Namaskar and good evening to everyone. A warm welcome to day 2 of our AICT ATAL sponsored online faculty development program on advanced antenna design for next generation wireless communication 5G 6G with AI perspectives. Before we begin today's session, let's quickly recap yesterday's session. Session 1 was delivered by Dr. Dharmen Singh Sir, Director at Triple IT Vadodara, Understanding Antenna Role of AI. Session 2 was conducted by Dr. Jaume Angure, IEEE Fellow and CTO of Ignion. Day 2 of session begin will shortly on the topic Machine Deep Learning in 5G 6G by Dr. Ahmed Al-Khatib, Professor at Arizona State University, USA. Session 4 will follow from 7:30 p.m. to 9:30 p.m. title From Smart Connectivity to Intelligent Universe from Journey from 5G to 6G by Dr. Vimal Bhatia, Professor at IIT Indore. We request all the participants to connect throughout the session. As we begin with session 3 of our faculty development program, we are honored to have with Dr. Ahmed Al-Khatib. To formally introduce our esteemed speaker, I now invite Dr. Saurabh Ghosh sir, Head of Department Electronics and Communication Engineering, Mahakal Institute of Technology, to kindly take the virtual stage and introduce the speaker. Over to you, Dr. Saurabh Ghosh sir.
Thank you, Dr. Mohit Pant. Am I audible?
Yes, sir.
Okay, thank you, sir. Firstly, I welcome our speaker, Dr. Ahmed Al-Khatib, and all participants in the first session of second day FDP. Dr. Al-Khatib received his BS and MS degree in electrical engineering from the Cairo University, Egypt in 2008 and 2012 respectively, and his PhD degree in electrical engineering from the University of Texas, Austin, USA in August 2016. From September 2016 to December 2017, he was a wireless communication researcher at the Connectivity Lab, Facebook in Menlo Park, CA. He joined Arizona State University in spring 2018, where he is currently an associate professor in the School of Electrical, Computer, and Energy Engineering. His research areas are in the broad areas of wireless communication, communication theory, signal processing, machine learning, and applied mathematics. Dr. Al-Khatib is the recipient of 2012 MCD Fellowship from the University of Texas, the 2016 IEEE Signal Processing Society Young Author Base Paper Award for his work on hybrid precoding and channel estimation in millimeter wave communication system, and the NSF Career Award in 2021. I request you, sir, kindly address the participants. Thank you.
Right. Thank you very much for the introduction, and thanks for the invitation as well. And thanks everyone for for joining. Let me try to share screen. Hopefully it will work first time. Let's see. All right, can you see the slides?
Yes, sir.
Okay, perfect. All right, so thanks again, everyone, for joining today. So what I would like to talk about today is machine learning for scalable MIMO communication systems. And let us start with motivation. And essentially, we'll talk about kind of different rules of machine learning and what and why this is important for scaling wireless communication in the future. All right, so if we start with some motivation, if we look now at the kind of some of the key trends in wireless communications is the use of large antenna arrays, which takes different forms from massive MIMO at low frequency to millimeter wave terahertz MIMO to cell-free massive MIMO intelligence services. So if you think about all these kind of key technologies, so they are all just trying to use larger and larger antenna arrays in different ways. And another key trend is the increasing dependency on higher frequency bands. So going from sub 6 gigahertz to millimeter wave and 5G maybe will be more adopted in 6G as well. and then sub-terahertz in 6G and beyond, and now also are looking at mid-band, upper mid-band, right, in 6G. So all these different trends, there's the use of large antenna arrays, the increasing dependency on higher frequency bands, they are mainly driven and motivated by the data rate. So people want to get higher data rates, so they increase antenna arrays or use higher bandwidths. But then the problem is that in order to really enable these interesting gains that come with these technologies and these trends, we need to overcome a number of challenges. So first, as we go to larger antenna arrays, the dimensionality of the channel matrix between the transmitter and receiver becomes large, which needs a lot of training overhead to acquire this channel, whether using like just channel acquisition overhead or beam training. So this makes it hard for these large antenna array systems to support mobility. It also makes it increase the power consumption, especially at the UE side. Another key challenge is the reliability and robustness of these links. So as we go to larger antenna arrays and as we go to higher frequency bands, the signal between, or the link between the transmitter and receiver becomes very sensitive to little mobility change and little and also to non-line of sight blockages, or sorry, line of sight blockages. So if we look at, for example, millimeter wave or sub-terahertz, so the signal has very high penetration loss, which makes this link very sensitive to blockage. So once the link is blocked by any object, almost it abruptly disconnects. So that makes it hard to maintain reliability and latency of these links. Also, as we go to larger antenna arrays, even at low frequency, so massive MIMO and larger massive MIMO and so on, this link becomes very sensitive to mobility, and robustness also becomes a challenge. So these are different types of challenges, and if we look broadly at these two sets of challenges, at least, we can say that acquiring the channel knowledge is a key for overcoming these different types of challenges. And so how can machine learning help in addressing these challenges and then enabling massive MIMO systems to scale in the future? So now I'll be looking at different rules of machine learning, and then every rule will kind of try to build the motivation and kind of a few examples. So one important rule of machine learning is its ability to learn complex mapping functions in general. And in the context of MIMO communication, we can think of this mapping as mapping in the channel space. So, and this is the concept that we proposed in 2019 under name channel mapping. So by channel mapping in space, frequency, and time, what we mean is if we have two sets of antennas serving the same user and in the same environment, then if certain conditions are satisfied, we can show that we can map the channel from the first set of antennas to the second set of antennas. In particular, if we have this setup, then we can define mapping functions from the position of the user to the channels at the first set of antennas, and also mapping functions from the user position to the channels at the second set of antennas. And these mapping functions are just given by just natural propagation of the signals. Now, if this condition is satisfied, so if we now assume that the mapping function between the position or the set of user positions, candidate user positions, and the channels at the first set of antennas, so not only at the first set of antenna, is bijective, meaning that there is one-to-one mapping, right? Or we can basically, for every user position, there is a unique channel matrix at the first set of antenna. Now, if this is the case, then this means that the mapping from the composite basically mapping exists, or step by step. It means that if this mapping is bijective, this means that the inverse mapping exists, meaning that from the channel, that there is mapping from the channel at the first set of antenna to the user position, and then by the second mapping here, this means that we can go from the channels to the position back to the channels at the second set of antennas, or directly, basically, we can go from the channel at the first set of antennas to the channel at the second set of antennas. And this is very interesting because this means that essentially once we guarantee that this mapping is bijective, then there is a mapping that exists between the channel at the first set of antenna and the channel at the second set of antennas. And this condition is actually not very hard to satisfy in practice. So in practical setup, so once we have 4 or 5 or 6 or 7, 8 antennas, this mapping becomes bijective with high probability. It's hard to kind of prove this mathematically, but there are also actually other studies that did some experiments and showed that this mapping is typically bijective with in many environments with a few antennas. So and this means that again, once we have a few antennas and this mapping is bijective, now we can go from the channel at the first set of antennas to the channel and the second set of antennas. But this mapping is typically, so even though like we can prove it exists, but it is hard to characterize analytically. So how we can learn this mapping function exactly. And this is where deep neural networks come to the picture as a way to learn this complex mapping function from the channels at the first set of antennas to the channels at the second set of antennas. All right, now this is good, but then what does this mean exactly from application perspective? So in fact, this concept could be shown to have many interesting applications in millimeter wave and massive MIMO. So if we look at some examples, so if we consider the special case when we are concerned about or interested in channel mapping in space, so which is a special case of this channel mapping. Now, basically, we assume that the two sets of antennas are at two different frequencies, but at the same space. So essentially, one is a subset of the other. So this is the case now in, for example, now you can think of massive MIMO and FDD massive MIMO. So the base station will do downlink training, and then the user will feedback back the channel. And typically, the base station needs to train all the antennas, and the user needs to feedback the channel at all the antennas, which needs a lot of training in the downlink training and a lot of feedback overhead. Now, if we use this channel mapping concept, then if we look at subset of these antennas at a subset antenna as a subset M1, and all the antennas as subset M2, then if we can show, or if we have basically a few antennas, then typically the mapping from this subset of antennas to the position, to the subset of antenna is bijective. So basically this first mapping is bijective. And once we show that, or once this is satisfied, this means that we don't need actually to train and feedback all the antennas. It is enough to only know the channel at the subset of antennas to be able for this neural network or this base station or this neural network that's running at this base station to say, okay, I mean, I will only train and feedback maybe 4 or 5 or 8 antennas. And then given that channel at this 8 antennas, I will predict that channel at the 64 antennas. Okay. So that saves a lot of training and feedback overhead. And again, of course, this neural network needs to be trained first, right? So you need first to collect data. So say in the beginning of the system operation, the system will work as normal, meaning that it will keep training and feeding back all the antennas. So now you have like all the channels. So the base station will keep accumulating these channels as the system just operates as normal without putting any extra overhead for the training. But now once the base station accumulates enough data set, then it will pick some subset, and you can also optimize to see which subset actually of these antennas will have the best mapping to this old antenna, and then train this neural network. And then once it's trained, now going forward, it will only need to train to downlink and feed and get the channel at only the subset of antennas to predict the full channel. So that can, as you see, like it can have a lot of interesting applications to, or interesting kind of gains to massive MIMO, FDD massive MIMO system. Another application that you can think of in the concept of channel mapping in space is in millimeter wave systems. So in millimeter wave systems, typically we have large antenna arrays, but we don't have number of RF chains equal number of antennas. So if we look at the extreme case, so we have an analog only beamforming. So we have a lot of antennas, but we have only one RF chain. So beamforming is done essentially in what we call the analog domain or the RF domain. So in that case, these systems typically use again analog beamforming to shape the beams. And one of the problems is that this for this link to be established between the base station, for example, and the user, typically the base station needs to do beam training or to sweep over large number of beams to find the best one. And if you now think of this concept of channel mapping, but in the beam space, so if this base station if this base station has two sets of codebook, two sets of beams, two codebooks of beams, one with wide beams and one with narrow beams, then you can think of this wide beam as basically a small, so say you have 180 degree and you can cover it with, say, either 180 beams, or maybe with 180 beams, each one with 1 degree beam width, or with maybe 18 beams, each one with 10 degree beam width. So, and what this mapping concept says that if you train this, if you just try the 18 beams, and then you learn the mapping from this, the power received by these 18 beams and the power received by the 180 beams, right? So again, mapping from effective channel essentially, which is the power at the complex gain received at this by this 18 beam and the 180. Then we can learn this map. Okay, this means again that instead of like the need to do beam sweeping over 180 beams, now we probably need only to do beam sweeping over 18 and then predict directly what is the best narrow beam that we need to use. In fact, this idea is now part of the release 18 and 19 study and work items under the name of beam prediction in space or spatial beam prediction. So in release 19 now is the work item, so beam prediction in space. So that's what is meant. Essentially, you do training with wide beams and then predict what's the best narrow beam to use. So you can actually look at the foundation of that, goes back to this channel mapping concept. You can also look at channel mapping in frequency. So in that case, these two sets of antennas for example, at two different locations, of course, need to be the same in the same environment, but they could be at two different frequency bands. And if we do that, so that's again another special case of this channel mapping when we look at different frequencies. So in that case, one example is TDD, FDD, but at two different say frequencies. So here the uplink could be at so the users do uplink training or uplink transmission at one frequency band, and then the base station can probably use this channel at the uplink, which is easier to acquire, right? So the user just send one pilot, the base station can estimate that channel at, say, the 64 antennas. But then the problem typically in FDD is that the uplink, the channel at the uplink frequency is different than the channel at the downlink frequency because they are two different frequency bands. But now with this channel mapping in frequency, we can learn how to map the channel at the uplink frequency to the channel at the downlink frequency. So the channel at the uplink frequency again is very easy to acquire. So the user just needs to transmit one pilot for the base station to acquire all the channels. The downlink channel is hard to acquire. So an easier channel to acquire, we can use it to learn or to predict a channel that's harder to acquire. Okay, so again, kind of the same concept. So we can also, in the previous cases, it was also always the case that you can use a channel that's easier to acquire to predict channels or beams that are harder to acquire. You can also look at this in the context of sub-6 and millimeter wave beams, systems, so dual band systems. And for example, if this base station is dual band and this user is dual band, and they communicate over both sub-6 gigahertz and millimeter wave, then again, the channel at the sub-6 gigahertz is easier to acquire, while the beam at millimeter wave is harder to acquire, right? It's harder to predict because you have a lot of beams. And also at sub-6, it's higher SNR. So it's a few antennas, higher SNR. So it's much easier to acquire the channel at sub-6. But this base station then can probably just estimate the channel at sub-6 between itself and this user, and then use this to predict what is the best millimeter wave narrow beams that I should use to serve this user. So this, again, we call this sub-6 to millimeter wave beam prediction. And if you're interested, also you can look at this journal paper where we kind of go into the theory a little bit more and some simulations and results. But essentially, the motivation is the same. So we use channels that are easier to acquire to predict channels or beams that are harder to acquire, saving a lot of training and feedback overhead, and then enabling these systems to scale a number of antennas and realizing their gains. Now, of course, this concept is, while it is probably interesting, but it has, if we go to first, the main condition that we had to make or had to assume in order to get all these interesting results is the bijectiveness condition between for the position to channel mapping. And as I mentioned, so there are some studies that show that this actually condition is satisfied with high probability once we have a few antennas. And of course, it depends on the number of antennas, array geometry, number of channel passes, and also all that affects how bijective this mapping is. But it is in practice typically bijective with high probability. Now, it's worth noting here that this actually condition is also the same conditions that we need to we needed to be satisfied for fingerprinting and localization. So also in order to use this channel to localize a user, this mapping has to be bijective. So it kind of is again, and since fingerprinting is already adopted in in even products now, so kind of this is probably a practical assumption to make. Now, another important consideration here is that this, what I presented so far, it kind of implicitly assumes a static environment. So once base station, once the first and second antenna sets are there, and the environment is fixed for different user positions, we learn these channel mapping and so on, and everything is good. Now, of course, once there is dynamic in the environment, then things get harder and more practical. And in that case, you can think of like generalizability across different dynamics in the environment. So we can train this model a lot to learn this mapping even and generalize across dynamics in the environment. But this may need a lot of training. So in a more practical setting, we then propose this idea of statistical channel prediction that we think is kind of taking this channel mapping concept into a more practical setting where instead of basically mapping exact complex channel matrices, here we map channel covariances and subspaces. We'll probably just move a little bit faster here, but yeah. So essentially, saying here in this particular example, we have two base stations. So base station 1 and base station 2, they are at two different locations, but in the same environment, and at two different frequency bands. So this is, say, uplink, and F1, and this is F2. Now, what we are interested in here is that, and this is a grid of users, and here we have actually dynamics, and this is part of the scenarios we have in DeepMIMO, which is a data set that I will also talk about briefly at the end. That's publicly available. And what we want to do here is, can we estimate that channel? So this user will send an uplink pilot, will estimate that channel at the uplink at this base station, and will want to use it to predict the downlink channel, what is the best beamforming, sorry, multi-user precoding actually that we should use for the downlink at this other base station. So we do like basically mapping across space and across frequency in the same time. And then what we do more specifically here is, again, we don't map the channel, but we map the channel covariance. So we say, okay, if this is uplink channel at this base station, what is the dominant downlink channel subspace, not channel, but what is the dominant downlink channel subspace, important dimensions in this space for this other base station to use. And then using this downlink channel subspace, then we can use this to basically reduce the dimensionality of the problem. So for example, if this is using a 64 antennas, can we use this uplink channel here to predict which of these 64 dimensional dimensions in the space are more important? So if we can realize, or we can narrow down this into the most important 8-dimensional, for example, subspace, then this means that instead of requiring 64 pilots, we probably need only 8 pilots to estimate that channel. And this saves a lot of course, training overhead. So again, it reduces the dimensionality of the problem, while also ensuring that now across this 8-dimensional subspace, I will actually do over-the-air training for the channel. So it's also much more robust. And I will not rely on machine learning to predict just the final channel matrix or channel vector. So it's kind of a compromise between training overhead and also robustness. So here we use machine learning to not to solve the final problem, but to reduce the dimensionality of the problem. So going from 64 pilots to requiring only maybe 8 pilots, and then using over-the-air training to an estimation and pilot estimation, just a classical solution to, but only in this 8-dimensional subspace to finally predict the final channel. So it achieves that two objectives. And here we look at how many pilots do we actually need. So if we predict the 5-dimensional subspace, we get here, if we predict the 7, the 9-dimensional subspace we get here, compared to the upper bound that assumes perfect knowledge of the channel. So if we perfectly know the channel at this second base station, this is what we achieve in terms of per user spectral efficiency as we have more users. Of course, as we have more users, the power allocated for each user reduces, and we have also interference. So the data rate reduces. But if we now rely on machine learning, we can get closer and closer. So I think this is kind of promising for practical realization of these gains. All right, now the second rule of machine learning that I'd like to talk about briefly is its ability to solve complex optimization problems. So the first rule is we use machine learning to learn mapping. And the second rule, we use machine learning to solve complex optimization problems that we can probably solve without machine learning, but maybe there are some limitations that prevent that. And in particular, one very interesting category of use cases in the context of MIMO is when we have limited observability to the channel. For example, if we consider the setup where we have a base station here and another one here, and then we have users. If this base station wants to serve this user, okay, and say it is in the receive mode. So this base station says there is an uplink from this user, and this is a base station in the receive mode. So it wants to ideally just receive signal from this user, but then maybe this other base station is transmitting if they are not synchronized, and then it will also receive interference from this other base station. So now if we want to design, if this base station that is operating at millimeter wave and practically using just an analog-only beamforming, if this base station wants to design its beam to maximize the signal to interference, then this problem is actually very hard. Why? Because if we consider this problem, now this base station has only, again, analog-only beamforming. So it doesn't know all the channels here. It only sees the projection of the channel on this beamforming space, on this beamforming dimension. And say we have the desired channel and the interference channel. Now, they are, again, since we, or if we look at the optimization problem here, is this base station wants essentially to solve this optimization problem. It wants to maximize the SNR, but subject to the constraints on the hardware. So it has only analog-only phase shifter, so that's hardware constraint. And assuming these phase shifters are also quantized, so this is another hardware constraint. Now, the problem here is that first, this problem, even if we know that channel, actually, this problem is an interesting optimization problem that's typically hard to kind of find a closed form solution to. But what makes this problem even challenging and more harder now is that we typically don't know these channels. So we don't know the channel at the user, and we don't know the channel at the interference. And even if there is a way to estimate the channel at the user, then the channel at the interference is, this interference is not cooperating, so it's very hard to know this channel. So how to solve this problem then? How to design this beam and how to optimize this beam in this problem? So essentially, how to solve this problem without assuming that we know the channels, that we perfectly know the channel, because in practice this is very, very hard to acquire. So without machine learning, actually, this problem is very hard to solve. But now with reinforcement learning and this kind of over-the-air interaction with the environment, turns out that reinforcement learning is a very interesting way to solve this problem. So essentially, to figure out this beam without requiring an explicit knowledge of the channel. And this is the very interesting point, is that even with very little information about this channel and the interaction with the environment, the reinforcement learning or machine learning can still iteratively figure out what is the optimal beam, or what is an optimized at least beam to maximize the SNR. So, and this this led to kind of this work that's actually now published. But essentially, the idea here is that we have this base station with phased array, and we have the beams, and then we don't assume knowledge of the user position. We don't assume knowledge of the interference, of course, position. We don't assume knowledge of the channel. So it's a very practical setup where really everything we know is that we have the phased array in this setup, and now we just run this algorithm without any prior knowledge to just try to do the following. So it receives the signal. The only thing is we assume is that we know we can get the receive power. We can basically activate our target user on and off, which is practical because we have communication with this user. So we turn it on, and we measure the signal plus interference plus noise, and then we turn it off, and then we measure only the interference power plus noise. So it's a very practical kind of types of measurements that we can get. And then just with this, we compute reward, and then this goes into an actor-critic reinforcement learning network that can predict what is the beamforming weight that should be here, and then we keep iterating till we converge into a beam that looks good. Now, this is very practical to the that we were able actually to just test it in the real world, and actually it worked for the first time. So, which typically doesn't happen, but the idea here is that, again, since this doesn't require any basically calibration for the antennas, it doesn't require any channel knowledge, and so it just learns and adapts the beam to the setup and to the environment and everything. So it was very interesting that we're able here to kind of run it in at ASU in a very practical setup where people were moving around, and we were able to achieve 10 dB SINR gain over this link. So here, just to be clear, so here we have a transmitter, we have an interferer, and then the camera is taken from the receive side, and this is what we achieve. All right, now in what we do, and this here is basically we took actually. So that was the intuition, that we learn basically a beam that maximize the signal, that has basically maximized the signal power, and then places nulls at the interference locations. But actually, to make this, to just kind of verify this intuition, we actually took this receive array after training to the anechoic chamber and measured the beam pattern, and found that it is actually it is kind of following what we asked. Sorry, connecting my charger quickly. All right. So this actually application has many interesting use cases. So for example, I mean, in another application we used, or another paper, we use the same kind of concept to also maximize coverage in non-line of sight and to optimize the beam shapes to the environment. So we can essentially, once this array is there and we train this or we run this model, then we can optimize the beam shape to the particular environment, to particular user distribution, to the particular interference. So that's what we call environment-specific or site-specific beam learning. So we learn how to optimize these beams to fit the particular environment, or to adapt to the particular deployment, the particular geometries, the user distribution, and interference. So it has many interesting applications, and for example, increasing coverage in millimeter wave non-line of sight, and adapting to interference, and so on. All right, another interesting rule of machine learning is its ability to now enable what we call sensing-aided or multimodal sensing-aided communication. So the general intuition is that if we look at, again, the channel between a transmitter and receiver, then we can generally say that the channels are defined by the various elements in the environment. So that includes the environment geometry, the locations, materials, and so on. So theoretically, we can write the channel matrix or vector as a function of the different elements in the environment. However, this function is hard to characterize analytically. And this is where multimodal sensing and machine learning come to the picture. So now, since this function is hard to acquire, then we can probably learn it. So we can have a machine learning model, or neural network, or deep learning model that basically takes these inputs, the environment geometry, the locations, the materials, and so on, and predict the channel. But then the key question here is that and of course the key kind of point here is that if we can acquire these inputs with low overhead without consuming many wireless communication or wireless resources, then we can probably use this neural network to predict the channel that needs a lot of wireless resources. So it's, again, kind of the same motivation. We use something that's easier to acquire to predict something that's harder to acquire. And this is where now the next question is how to actually acquire knowledge about the transmitter locations, receiver locations, geometry, shapes of the environment, scatters, and so on. And this is where the different sensors come to the picture. So multimodal sensing, all the way from position sensors, visual sensors, LiDAR, radar sensors, and so on. So all these different sensors provide a lot of perception about the environment that can help us and basically acquire this knowledge and predict these different channels and then different decisions on the communication network. Now, interestingly, as we go larger in antenna arrays and as we go higher in frequency bands, like the two key trends I mentioned in the beginning that make actually acquiring the channel harder. Now, as we go to larger antenna arrays and as we go to higher frequency bands, in the same time as the channel again gets harder, channel acquisition gets harder, but in the same time, the channel dependency on the locations and environment and so on becomes actually clearer, which makes basically gives higher value and higher advantage and higher motivation to relying on sensing. So that's kind of interesting. So the role of sensing becomes more and more dominant and more useful as we go actually to larger antenna arrays and higher frequencies. So kind of it's a natural kind of, so essentially it's a problem, but in the same time, if we use the sensor, so we kind of solve the problem in the same way. So I mean, going to higher antenna arrays and larger antenna arrays and higher frequency bands, it poses a problem, right? But in the same time, it also opens, a way to solve this problem. So it's a very interesting, concept to think about. And this makes like the knowledge of position geometry and mobility patterns, as I mentioned, more useful, especially as we go to kind of these regimes. And this is a motivation for what we call multimodal sensing aided wireless communication, where we envision that in the future infrastructure side units and user devices will have different types of sensors from not just GPS, but also LiDAR, camera, radar, and so on. And all these sensors will extract a lot of information about the environment from user position, scattered positions, orientation, shapes, mobility patterns, weather conditions, and so on. And then all these different sensors sensing information, and this information will provide a lot of awareness to the communication network that it can use to make the different types of decisions on where to point beams, how to estimate the channel, where if there is a blockage coming or not in a proactive way, maybe, and how to use this to do user scheduling, user clustering, code book design, resource management. Really, all almost like everything can be revisited from this lens of how this awareness that we obtain from multimodal sensing can help us now make more informed decisions. So it's a lot of interesting applications. And in order to enable the research, now if we want to do research in this direction, we need to have data of a special type. So we need to have data sets where in the same time we have the communication channel, for example, we have also the sensing data, right? So we need this sort of coexisting sensing and communication data to be able really to investigate, any of these interesting problems. And with this motivation, so when we looked at this, when we started working on this problem, there was no data set, and that's why we built DeepSense 6G which is based on real-world measurements as a data set with coexisting multimodal sensing and communication. And we have now over 1.5 million multimodal data points, again, covering different use cases from V2I, V2V, RISs, indoor and outdoor drone scenarios. And so kind of looking at different use cases and then extract and then collecting data, always the same format. We have the multimodal sensing, we have the communication coexisting, synchronized, and now we can use this to do a lot of things. So if you visit deepsense6g.net, then you will find the dataset publicly available. We have over 44 scenarios now, and every scenario we have such videos that we kind of show the different modalities in the full actually scenarios. You can look at the full scenarios. You can use it for debugging or for getting some familiarity with the scenario and so on. We have of course the data as well of all these different modalities. So that's, for example, a V2V setup. So here we were driving across different cities in Arizona, and actually we have also now contributions to DeepSense from other universities, and I encourage you as well, if you are interested, we'll be very happy to host your data as part of DeepSense. So and then of course with credit kind of linked to these data sets. So So DeepSense is structured in a way that is as scenarios. So basically, if a university is interested, they can contribute with the scenario. So we just work together on interfacing the data to be on the DeepSense format, so that anyone that's familiar with DeepSense will be able to also access this scenario. So it's a couple of a win-win situation to the community, researchers, everyone. All right, so now with DeepSense, we hope it can now enable many interesting applications in wireless communication, beam prediction, tracking, blockage prediction, resource management, and so on, but also to positioning and ranging. And then I think more interestingly is now that we have this large data set with sufficient diversity over many locations, many environments, we can now use it to study a lot of interesting machine learning problems in transfer learning, fusion learning, data fusion, and so on. And also it facilitates benchmarking. We have been using DeepSense to organize a number of competitions because now we have the same, again, said that the same ground that people can, like compete on different problems using the same data set. And so it enables benchmarking and reproducibility. In fact, if you visit deepsense.net, then you will find also a tab in, we have tasks, machine learning tasks. Under this, can find probably 8 or 10 different tasks that that you can participate to. And so we define the training and test set and so on. So if you try to solve this task and submit your results, so you get ranked in this ranking table. So for example, this is one where we have different contributions from academia and industry. All right, so this is one demo that we have where we show, for example, position to beam. So here we know, vision to beam. So here we have the visual data, and we use it to do beam prediction. So again, it goes along this line of just one of the applications in DeepSense. And again, if we look here, so one of the key takeaways is that here we are using just visual data and actually position data. Both are non-wireless. They don't need wireless resources to acquire, almost. Right, assuming this camera at the base station, so it doesn't need any transmission over there, and this only the position is communicated. So it's almost without using any wireless resources. This base station that has 16 antennas and 64 beams is able to accurately point the beam towards the user and do tracking for the user, even in the existence actually of other what we call distractors or other users in the environment. And what this shows is, again, this idea of scalability, that now we didn't need to use wireless resources to train this, to find this beam, and which means that even if we scale this number of antennas, we can still probably do the same. Or practically speaking, I think we'll be using, again, machine learning not to solve the problem, but to reduce the dimensionality of the problem. So instead of requiring, maybe if you have 256 elements and a phase array, instead of requiring 256 beams, now probably we can reduce this to, say, with this visual data for the base station, can say, okay, maybe these are the 8, 10 beams that I should probably use because the user is in this kind of area. So it reduces the dimensionality of the problem. Now, maybe the base station needs to do fine tuning only over 8 or 10 beams over the air to find the best one. Yeah. So this is, I think, is very promising for the scalability of MIMO systems and the higher frequency, and enable us now to kind of use millimeter wave and higher frequency bands. All right, now, for sake of time, so I will just go over other problems that we have studied or others have studied, and we have papers and code and data on DeepSense.g/ publications. So you can find all these publications there. But we have you can use DeepSense to look at V2V beam prediction. It's very interesting. So can we, as a user, as the vehicles move, can we still keep the beams basically aligned? To look at drones, we have even data coming from drones, like an actual drones, and can we use it to do higher mobility tracking for the drones? We also used DeepSense to look at what we call proactive blockage prediction. For example, as I mentioned also in the beginning, so line of sight blockages is a big problem to millimeter wave. So if the link is established, and then if there is any blockage, the link may be abruptly disconnected. So can we use, if there is a way to proactively predict these blockages before they happen, then the network can probably use this time to do proactive action. So it can maybe switch this link, this user to another base station, or switch to another beam that's probably more non-linear side, but still at least will stay available. as this blockage happens. So this proactive prediction of blockages can have many interesting ways. And this is where also, like, so here what we did is that we looked at this deep sensing. In fact, here what we use is just wireless data. So N-band wireless sensing, okay, another sensing, basically one of the sensing modalities, to and then machine learning and deep learning to learn some patterns as this, for example, this bus, as it gets closer to this link. In fact, even before it blocks, it introduces some scattering pattern in the wireless data that if we can learn, we can maybe proactively predict that this bus is going, or there is something that's going to block the link. And even if that is like, whatever, 40, 50, 100 milliseconds, then this is still a very valuable time for the network to make some proactive action. So that was the motivation here. We have a journal paper that talks in detail about all these different experiments. Now, another application is what we call distributed multimodal sensing and communication. So here, if we start taking this concept of multimodal sensing aided communication to a realistic setup, so the network will not really, it's hard to scale this without, while assuming that every base station or every node will have its own sensors, and it will rely only on its own sensors. So because this will not, first, I mean, the coverage or the range of coverage of line of sensing is different than communication. So for example, a camera could probably go to 100 meter, a radar probably also the same, a little bit longer or shorter depending on the quality of this radar. LiDAR is the same. So, but communication networks, they can go probably to, you know, a few hundreds of meters and millimeter wave, and probably kilometers and lower frequency. So, so how to kind of bridge this gap, or to kind of address this difference in the coverage of sensing and communication. So one way that we thought about is to that eventually, I mean, as we go from just, you know, demo or a little toy example to a realistic network, I think eventually we'll need to have distributed sensors serving communication. So there will be like a network of sensors, multimodal sensors, in different locations in the environment. So they collect a lot of information about line of sight, non-line of sight objects, and so on. And then this network of multimodal sensors will be supporting not just one base station, but many base stations. So, so this takes us to kind of this idea of distributed multimodal sensing aided communication, where there are different sensors that will be helping the communication. And then this actually raises, so it solves one problem, but it also raises other interesting problems on, now that we have these multimodal sensors, how this data will actually be transmitted now to the communication nodes without consuming many wireless resources. Because if we are all trying to use this multimodal sensing to help the communication, now all of a sudden now all these multimodal sensors are also introducing a lot of traffic, right? So so there is like an interesting trade-off here between sensing and communication, and this also makes it like very interesting to look at problems like what we call environment semantic communication, for example, that we probably don't need to kind of capture and then transmit all the raw sensing data to the base stations. Maybe this sensor, these nodes can do some sort of extracting only the semantics that this end communication network is interested in, and only communicate these semantics to reduce this communication overhead between these multiple sensors that are distributed and the communication node. Maybe you can do some sort of distributed learning, federated learning. So all these like interesting now directions become very, again, promising for research and open really new research directions. All right, so the fourth and last role I would like to talk about is the role of machine learning in enabling what we call real-time digital twins. So now again, assume there is this user moving in the environment in a city, and it wants to connect to this base station. So for this link to be established, and assume this base station has a massive MIMO antenna array, say 64 antennas. So now if we don't use any sensing or anything, so this base station and user again need to establish some sort of like beam training or channel acquisition that requires typically a lot of pilots for this link to be established. Okay, now if this user uses its multimodal sensors, it will only have access to the line of sight information. So it's not enough to also connect to this non-line of sight base station. And this now raises this kind of interesting opportunity to leverage not just the multimodal sensing, but also the 3D maps of the environment. So now assume that this user is moving in this downtown, for example, and it has access to the 3D map of this environment. Then, and including also the location of this base station antenna array and so on. So then we can, and then assume now also that this user has multimodal sensors that capture not just static, but also now the dynamics in the environment, even if just within its point of view. So now, if that is the case, then at least theoretically, we can run ray tracing. So this user can run ray tracing somewhere. It knows the environment, it knows the location of the panel, of the antenna, of the base station. It knows the environment dynamics and so on. So probably it can run some sort of ray tracing or propagation modeling or evaluation simulation. And then based on that, it acquires the channel between itself and the base station. And then it uses that to now directly connect to the base station. Now, practically speaking, we can, I don't think we will ever be able to, this user will be able to get the exact channel matrix, the 64-dimensional channel matrix or vector, but it can use this digital twin to acquire at least some dimensions, some information that would reduce the dimensionality of the problem, which I think now is becoming more practical. So, for example, this user can use this, say, ray tracing to acquire knowledge about what is the dominant dimension of this channel. So what is the most important dimensions or directions that I should point my my receive pilots from, or this base station would also figure out what is the important dimension for this user to focus the signal power in this, say, downlink training too. So it can just reduce the dimensionality of the problem and make it more practical now to also in reality. And this is what this motivates what we call real-time digital twin. In fact, we proposed this in 2023, this idea of real-time digital twins of the environment. And at that time, so just 2 years ago, I mean, it was, we felt it's probably very futuristic, but we were excited to see that kind of the different technologies are all actually, if we extrapolate them, all intersecting in this digital twin. So we realize that there is precise 3D mapping is becoming more and more accurate. Multimodal sensing is becoming more distributed and more ubiquitous, right? So you have them at the infrastructure, at the users. Now infrastructure in 6G will likely use radar, at least, probably cameras. So if we project this multimodal sensing on the precise 3D maps, then we get basically more like real-time 3D map. And then also we saw like ray tracing becoming more real-time. In fact, companies like NVIDIA and also Remcon, and ANSYS and others are now promoting real-time ray tracing in commercial grade. So if we run real-time ray tracing on real-time 3D map, then powered with machine learning to activate everything, then if we extrapolate a little bit in the future, having real-time ray tracing on real-time 3D map to have real-time digital twin does not look as futuristic as it initially looks. So based on that, kind of we proposed this idea in this magazine, and just 2 years ago, that now it's probably becoming more and more popular. So to kind of look at digital twins in different wireless environments. So anyway, so if we it's becoming more and more interesting to realize this game that if you rely on 3D map, if you rely on multimodal sensing, and if you rely on ray tracing, then having this idea of digital twin may not be as futuristic as it may look. And we're surprised to see like actually industry were getting interested in this work even before academia. So we published this magazine, and then we found a lot of interest from industry, interest in kind of collaborating with us on taking this to next steps. And then after that, academia, realized this value. So it was kind of interesting to see this kind of slightly different trend from what's expected. Typically, academia leads quickly, and then industry follows. But yeah. So now from this digital twin, you can also think of like different models. So you can think of like one level where every device may have its own digital twin living either on device or edge or cloud, depending on its latency requirements and compute availability and so on. So every device could have its own kind of local digital twin that it feeds with its own sensing data and use it itself. Or you can think of a more interesting scenario where multiple devices in the environment, they somehow subscribe to a global digital twin, maybe living at the edge of the network. And then they feed this network with this digital twin with their sensing, so that they build a more kind of complete digital twin. And then they use it separately to make their own decisions. Or you can think of like a more, again, maybe complete or more complete, which is vision, where these different devices subscribe to, and maybe base stations as well, subscribe to the same digital twin. But then they feed their sensing data, but they also use this digital twin to make joint sensing and communication decisions. So now they make joint sensing decisions. For example, if two users are close, they probably don't need to sense the same environment again. And if, again, the network can probably use this to make different coordination decisions between the different users in the network. So this is more like towards, we called it here level 3, which is more shared information and communication decisions. All right, now, how can we use these digital twins in practice? There are different ways to do that, but in general, you can think of the digital twin as a model for the environment, and a model for the hardware, and a model for the propagation. And if we have the 3 models, we can probably have an accurate model of the environment, of the wireless channel, or the digital twin that we can use to extract wireless channel. And this could have a lot of interesting applications, to all the way from physical layers. So we can use this digital twin to do channel prediction, link adaptation, to help with beam management, to help with network configuration, to help with proactive caching in the application layer. So really all the different layers in the communication stack could benefit from having this environment digital twin that extract a lot of information about the environment. And now machine learning is, of course, a key here. So in almost all these different tasks would leverage some sort of machine, either the construction of the digital twin may be done over machine learning, so we can learn how to calibrate these digital twin and how to make them more closer to the real world, and how to close the gap between the digital twin and the real world. We can also use machine learning to learn how to leverage the outputs of these digital twins to make this, important and accurate decisions. Yeah, so now if we want to do research in digital twin, we need also, again, to have this synthetic and real world, or the digital twin and the digital and physical replicas. And that's why we built DeepVerse-XG. It's another data set that we built with scenario. And in fact, now it's kind of, this slide is a little bit outdated. This DeepVerse is now available, so you can visit deepverse.xg.net and you will find the data set where we have we built DeepVerse to do 2 things. One is it enables multimodal sensing and communication in a larger scale, because we have synthetic data. So now we can kind of make it like more broader and address more scenarios. But we also built some of the scenarios, we call this virtual scenarios. And then we also built digital twin scenarios to the real world scenarios we have in DeepSense. So in DeepSense 6G, we have real world data. In DeepVerse-XG, we built some of the scenarios to be actually digital replicas to the scenarios in DeepSense. For example, this is DeepSense scenario 1 here, and we built DeepVerse scenario 1, which is digital twin 1, which is a synthetic version of this. So it's not just actually capturing the texture of the visual scene, but we also try to match. Sorry, are you still? Not sure what happened. Can you still hear me?
Yes, sir.
Yeah. Okay, perfect. So so we built, yeah, so again, so we didn't just match the texture of the environment, but we also modeled the wireless, and we tried to calibrate the wireless environment as well. For example, here we take the phased arrays that we actually use to measure the beams, for example, in transmit and receive beams, and in the DeepSense, and we modeled it in the anechoic chamber, and we use this model in the DeepVerse. So it's kind of, we tried to basically move the models of the different aspects, the geometries, the hardware, and so on, to the digital twin. And this is the result. So here we have, this is scenario 1. So here we see the real world visual data, wireless data, and here we see the digital twin visual data and wireless data. So actually this beam we got completely from the digital twin, and as you see, it matches very well the real world. Now, of course, the advantage in the digital twin is that we don't have noise, right? So you can actually use this to study what is the performance, say, at different SNRs and different distortions. So if you have the clean data without distortion, you can easily distort it. If you have the distorted version, you cannot like clean it, right? And we have also LiDAR, we have radar, so all synthetic and real world. So you can now study, okay, can we use it, for example, radar digital twin to train a model that you can use it now in the real world and so on. Now, from application perspective, I think there are two main ways to use digital twin. One is online, one is offline. So you can use it first offline. Let's talk about offline first. So you can use this digital twin as a way to extract data and collect data about the environment, site-specific data that you can use to train different machine learning models. You can also use this digital twin as an environment that you can interact with. For example, this beam learning, if you remember this example of reinforcement learning that I presented in the second rule of machine learning. So the base station needs to interact with the environment to kind of configure and figure out the best beam. Now, this, if we actually want to do that over the air, the downside as a disadvantage is that we need a lot of interactions with the environment, so probably hundreds of interactions. So which could probably be seconds. I mean, but if this is a system that's running, so consuming, like taking seconds to actually figure out the beam could also be concerning. Now, with a digital twin, you can probably run this beam learning over a digital twin of the environment to at least narrow down again to again reduce the dimensionality of the problems. You can maybe figure out at least an initial good beam and then do more steps over the air. So probably instead of requiring 1,000 iterations, now you probably require 100 iterations to find the best beam. So this is one use case of digital twin where you use it offline. Now you can also use it online or real time. Now, of course, by real time, I don't necessarily mean like exact real time, but it could be near real time. It could be, so what I mean by real time in general, digital twin, is that these are digital twins that we can use to make to make some prior, right, to extract some priors or to generate some priors to the actual system operation. So as the system is actually operating, it can leverage these insights that's coming from the digital twin to make better decisions for user scheduling, for channel prediction, for beam prediction, for localization, for many interesting applications. And we also looked at many of these interesting problems in our research in the last year or two. So I will kind of just move quickly, but because of the time. But if you are interested, so we have all the papers and the code and the data on our website. And of course, we'll be happy to answer any questions you have also over email. So we looked at digital twin for beam prediction. Can we use digital twin to pre-train basically a machine learning model that using the position, it predicts the beam, and then use this in the real world? So kind of it saves some training overhead. We also looked at CSI acquisition. So that's joint work with Nokia and Bell Labs. And here what we do is, can we use the digital twin to generate channels and train a CSI compression, decompression codebook, model, and then we use this model in reality. So it reduces the amount of overhead that we need to collect the data in the real world. And here also we looked at an important aspect, which is the fidelity of the digital twin. So it's not always, so there is always, like in the digital twin, there will be like a trade-off between cost and gain. So if we have a digital twin, so the construction and maintenance of this digital twin needs resources, different types of resources, maybe wireless resources or compute resources and so on. But then to increase the fidelity and accuracy of the digital twin. So accuracy and fidelity of the digital twin comes with cost. But then it has some gain, right, depending on what I will use this digital twin for. And there is always this interesting trade-off between the cost and the gain. And in fact, it's not always, so if we plot the cost over gain versus fidelity, it's not always like, it will not always keep going up. So there is diminishing returns at the end. So as we make this fidelity higher and higher and higher, at some point, more fidelity doesn't basically help. I mean, it's not, it may not hurt, but it may not necessarily help. So, but it will add cost, right? So there is like this interesting trade-off that compromise between, okay, so what is the right fidelity level that I should have my digital twin at in order to have reasonable cost compared to the gains that I want. So there is like this, I think, always this optimality point when we think about digital twins for different communication sensing tasks. So in this particular paper, we tried to look at, which is journal, will be available on arXiv soon. So here we looked at different fidelity aspects. So geometry of the environment, the EM material and knowledge, the ray tracing, and we looked at like what is the impact of every fidelity aspect on the digital twin. If you're interested in this paper, actually, I'll be happy to share it with you also over email. So hopefully my student will post it in arXiv in the next week or two. So, and this is another work that we looked at digital twin for channel estimation. So if we have, again, digital twin, the space station probably can use this digital twin to know what is the dimension, what is the best subspace of the, or the important dimension, low dimension subspace, and then use this information to reduce the channel estimation overhead. So here we were looking at this problem. And then also we looked at digital twin for positioning. So that's a very interesting application. So positioning with fingerprinting typically needs to collect a lot of data from the environment, which is expensive from manpower perspective. So now, can we use a digital twin to pre-train to generate a lot of the synthetic data, RF maps, and then use these RF maps for the real world to make localization decisions? So here we had this kind of initial work that showed some interesting promise. And then we can also use digital twin actually for ISAC decisioning. So not just for communication, but also for sensing. And probably counterintuitive, but the gain of digital twin for sensing could probably be even more than communication. So having this knowledge of the environment could be very interesting for sensing, for making sensing decisions. And the reason why it's more interesting than communication to me is because communication, you have basically both the two sides of the link, if you wish, like they can speak, right? They can transmit data. So the base station or the access point and the user, both of them can transmit it. But in sensing, the target typically doesn't transmit things, right? So then you have, for example, a user that is, or a target here that you want to sense. And so having this knowledge of the digital twin can typically help in making maybe designing code books or making different sensing decisions that can help the sensing performance. So, for example, in this particular initial work that we published in last SLMR, we were looking at, last SLMR. So we were looking at how sensing can help, how digital twin can help designing sensing beam. And in particular, we just noticed that if we just know whether this user is line of sight or this target, sorry, is line of sight or non-line of sight, this can decide whether we should design the sensing beam in one way or the other. And just knowing this knowledge or this information about line of sight or non-line of sight can help make actually a significant gain in the performance. So we have this paper in the code, again, published, so if you are interested. And it could also be, digital twin could also be very interesting for spectrum coexistence and sharing. So if we have licensed and unlicensed networks, and for this user that's unlicensed, just knowing its digital twin, it can help it make beamforming decisions, for example, to manage the interference to this licensed base station. Without digital twin, this user, this unlicensed user, typically needs to wait till it makes sure that the licensed network is not used, and then it transmits to its unlicensed base station. But with the digital twin, it can make much better and smarter decisions. All right, now, we also looked at it for CSI or compressive sensing dictionary learning. So it's again another interesting direction. Okay, so what I want to kind of highlight now in this last 5 minutes is important considerations when we look at machine learning and wireless communication networks. So 2 or 3 considerations. One is, it's very important in many of these machine learning gains to really shine and to be clear, is to use, for these gains to be clear, it's very important that we train these machine learning models based on site-specific data. And this is one of the issues that we see, especially industry is making, like they build machine learning, but then they trained it on stochastic data, which just doesn't have what we call spatial consistency. And then they don't see the gain. So maybe there is a problem that actually machine learning can't realize a lot of gains if we actually deploy this in practice. But just because we didn't use site-specific data that's preserving the spatial consistency of users that are close together and so on, then we may not see these gains. So and this is why it's very, that's actually the motivation why we built DeepMIMO dataset in 2019. And we are still maintaining it, and we're releasing a new version soon, and out of beta version. But essentially, DeepMIMO is a way to generate site-specific datasets based on accurate ray tracing. So it takes a ray tracing scenario, and then you can assign parameters to say how to where to place the users, or select users, which base stations you are interested in. You can configure the array configuration at the base station and users and so on. And then with these parameters, DeepMIMO generates the channels. So it generates a channel dataset. Now, the important thing here is that first, this channel that's generated by DeepMIMO is completely defined by which ray tracing scenario you picked and which parameter set you configured, which makes it easy to define and easy to reproduce. So once you mention, I use DeepMIMO with these parameters and these scenarios, then anyone else can generate exactly the same data set, compares with exactly your data. And this is very important for the reproducibility of the research. The other advantage is that, again, it's a very easy way to, because we have pre-generated all these ray tracing scenarios. So now, really in minutes, or probably in seconds sometimes, you can generate a data set. You can generate hundreds or thousands or tens of thousands of data points in minutes using DeepMIMO. So that's another advantage. And then now, as you will say, I will talk more about DeepMIMO in next few slides. You'll see more interesting things. And the third thing, of course, is that it is ray tracing based. So it's preserving spatial consistency and site specific. So these were kind of the motivations for us to build DeepMIMO some years ago. And now it's widely used by industry and academia. And for example, I mean, about site specific training. So here, if we look at, we looked in this paper on one example, which is CSI compression, which is one of the, like one of the important use cases that are being studied in industry and standard GPP. Can we use deep learning essentially to know how to compress the channel and to reduce the feedback overhead? So here we see a lot of gain as we go from, if we just don't look at any, if we don't use site-specific data, or if we use site-specific data, or if we even go to what we call zone-specific. So by not just like dealing with the full site as one data set, but we can even divide the site into zones. And then every zone, we can train a model for every zone, or we can learn this zone-based somehow. So, and we see a lot of gain, again, as we go from site-specific, from non-site-specific to site-specific to zone-specific. And this kind of, again, raises this idea that unless we train our machine learning models with site-specific data sets, then we may not see big gains that are already there and make misleading decisions. So that's why it's very important. And with this motivation, we built DeepMIMO v4, version 4, which is now available in early access. Actually, if you are interested, you can go to deepmimo.net, and you can just add your email and get an early access to DeepMIMO v4. So in DeepMIMO v4, we extended the support now to Shiona, NVIDIA Shiona, NVIDIA Ariel SAM, or AODT, and we have so we can convert from any of these ray tracing to a DeepMIMO format, and then use DeepMIMO now to kind of also connect to any of these linked and system level simulators. So this makes it interesting, because now we also open source the converter. Everything here is open source, so we open source the converters and integrators. So you can, if you generate a scenario, say with Shiona, now with one line of code in your Python, say, environment, you can convert this Shiona scenario to a DeepMIMO scenario. And then you can also contribute this scenario on DeepMIMO. So now with your APIs, with our APIs, you can just push your scenario to DeepMIMO database. And with your paper, now, so anyone that, and then gets listed on the DeepMIMO scenario table, and then anyone uses the scenario will cite your paper. So it's kind of, it's becoming more like a community database for the DeepMIMO for data sets. We have now more than 150 scenarios, and it's getting actually now kind of more adopted by AI RAN, NVIDIA AI RAN, and industry. So yeah, I mean, we are excited about that. Another consideration when we talk about machine learning is what we call foundation models. So it's, if we have a complex task, where the input say is channels, then typically we would feed this channel through some machine learning model to learn this complex task and get some performance. So this is the performance versus dataset size. And if this task is complex, then typically we need a lot of data to learn this complex task, or to train the model to learn this complex task. But now with what we call LWM, or large wireless model, foundation model, what we found is that we can so we have we released this LWM 1.0 and 1.1. Now you can also again find them on lwm-wireless.net. And you can download. So this is a pre-trained, basically foundation model. So think of LLM, but for wireless. Okay, but this is not an LLM model. We trained it from scratch based on just wireless data. So it's also very small in size. But if you basically download this pre-trained LWM models that we trained it on many data sets, then using that channel as an input, it generates embeddings. And if you train your complex task based on the embeddings, then typically you get much better performance with less data. So that was performance, for example, if you use just the road channel. Now, if you use LWM-based embeddings to train the same actual downstream model for the same task, you typically get much better performance. So it serves in many applications. So I have also actually another talk that just focuses on that. If you are interested, let me know. I'll be happy to share this video of this talk with you. But yeah, probably for sake of time, I will move faster here. But essentially, we have this foundation model published on lwm-wireless.net, also on Hugging Face, the model. And yeah, again, on the website, you will find many resources that talk about that. And probably skip this for now. Another important consideration, again, is this idea of, if you think of machine learning as a way to solve the exact problem, then this may have a lot of risk from robustness perspective and scalability perspective. So machine learning may not be very good in predicting complex values. So, and many of our in our communication tasks, we need like channel prediction or channel knowledge. So, and this may make machine learning less interesting. But I think what is more practical is to think of machine learning as a way to extract prior and reduce the dimensionality of the problem. So you use machine learning to again, to maybe in a beam prediction task, you can use machine learning to know what is the most important 4 or 5 dimensions of 4 or 5 beams, instead of like training over 64 beams. Or in channel prediction, as I mentioned, so you can use maybe channel deep learning or machine learning to say, okay, this is probably the important dimensions of the space. Or you can use machine learning and user scheduling to narrow down on important users, and so on. So thinking of machine learning as a way to generate priors and reduce the dimensionality of the problem, and then use over-the-air training and classical work and classical solutions and algorithms to actually converge into the final channel or beam or user scheduling and so on, then I think this hybrid approach is probably a more scalable approach. From one side, we still use deep learning and machine learning to kind of help us with the problem, but at the same time, we are also kind of ensuring robustness. All right, so I already presented this. So with that, I conclude. So machine learning is important for scaling MIMO and scaling the possibility to use higher frequency bands. And then we saw different rules of in learning complex mapping functions and solving complex problems and enabling directions like multimodal sensing and digital twins. But there are important considerations. And as I mentioned, we also published a number of data sets that you can probably leverage to address some of this research in deep MIMO and deep sense. We have all our papers actually in our group. So if you are interested in looking at any of these papers that I presented deeper, so you can go to wirelessintelligencelab.net and wi-lab.net, and there you can go to research and you will find all the papers. All the papers, we have the code and we have the data, so you can reproduce the results and play with it more. Okay, with that I conclude. Thank you, and looking forward to your questions. Right, any questions?
Thank you for your enlightening presentation, sir. Any query from the participants? You can turn on your mic and speak. So there is one query on the chat box. How channel mapping will work on dynamic cases?
Yeah, excellent question. So as I tried to kind of highlight, so in dynamic case, here actually this was a dynamic case. So if you have dynamics, you cannot like use, I think like, so you need to think of a statistical sense in that case. So as I showed here, so we can use, yeah. Yes, so you can think of channel mapping now in statistical ways that you predict channel variance, not channel matrix. And I think this makes it like robust to dynamics. So here actually we had a dynamic scenario. So these stars and buses were moving while we collected data and run this through the system. All right.
Any other queries? Sir, in DeepMind, how we can generate the data set?
It is actually very easy. You go to deepmimo.net. Let me see, maybe, or anyway, so yeah, so let me try to give you a quick demo on how to do that. Okay, so can you see this? I think. Can you see this?
Yes, sir.
Yeah. Okay. So this is a DeepMind website. If you go, just add your email, you'll get an early access to it, and then so the way to use DeepMind is that you can just go to the scenario page. This is one way. Okay. So you will find a lot of data sets here. You can download one of them. For example, you are interested in this data set and this scenario for ASU campus. Okay, so you can, here you will find more information about this scenario and how we generated, what ray tracing parameters, what's seen, and so on. And then you can download this file. So this file is pre-generated already, the ray tracing. So we have already done the ray tracing. And then you can go to get started. And then you can, as a user, you can now do pip install pre-DeepMimo. So that gives you now the DeepMimo package. And then if you want to, then you basically in your Python script, you will import DeepMimo DM, and then DeepMimo generate this scenario. And that's it. Now you will get a data set. You may actually need to do load first, so depending on the case, but yeah, import DeepMimo as DM, load the scenario, and now you have access to the data set, and you can generate the channels. Yeah, so again, very simple. And then actually here you can find, if you would like more like step by step. So in DeepMimo in help, DeepMimo in tutorials, you will find my student giving like a step-by-step tutorial on how to use DeepMimo. And then we have also Google Colab codes that you can follow along. Yeah, so how to use DeepMimo, how to use it for visualization, generation. We have actually a visualizer here that you can use to also kind of visualize, like ray tracing and how these trace. And yeah, so again, in literally minutes, you can have a data set with DeepMimo, and that's without needing any, like basically with just your Python environment. That's all.
Thank you, sir. So another question: what algorithm used in GPS receiver?
In GPS receivers? No, so in which work? Like you mean in the data collection or in position aided beam prediction?
You asked by Yajini. Madam, are you there?
Yes, sir. Yes, sir.
Can you explain the question to sir?
Sir, for beam forming for GPS receiver, so what type of algorithm is in?
Yeah. Okay.
Yeah.
Yeah, sure. So maybe share again. So I think you probably. Yeah, so you probably are asking about yeah, maybe one of these like works. So for example, I mean here, what we do is we use okay, yeah. So here we use position to predict beam. Okay, and what we use here is, yeah, I hear some noise. Hopefully you're still with me. So so here what we do is we use the position of the user to predict what's the best beam. We actually tried different approaches. So if you look at this paper, we looked at different ways. So we looked at you know, like fully connected network or even just simple algorithms. But in this problem, we're actually not looking at kind of how to optimize algorithms that much on how to do position to beam prediction, but on how to use digital twins to do that. And another, so how to use digital twin to reduce the amount of data that we need in reality to train these models by relying on digital twin. We have, however, an earlier work where we looked at how to do position to beam mapping using different like approaches like KNN or a neural network or just lookup table, and we compare between these three different methods, for example. So if you use like a very simple lookup table based approach for positioning, then what's the performance compared to using, for example, neural network? And we kind of, that was actually some work with Qualcomm that we have done 3-4 years ago on these different cases.
So based on the lookup table, we can choose it. That's
so you can do that based on lookup table, or you can use that based on neural networks. Right? You can have a neural network that takes a position and predicts the beam. Right? So you can train this model that, okay, when I have this position of the user, that was the best beam. When I have this position, that was the best beam, and so on. And then this neural network will learn that this kind of nonlinear mapping between necessarily, you know, it's not necessarily linear, right? So to learn this maybe nonlinear mapping between the position and the beam, and will learn this basically manifold.
okay, sir. Thank you, sir. Thank you very much.
Thank you. I think you're on mute.
Thank you, sir. On the behalf of all the participants and from MIT Group of Institutes, I extend my heartfelt gratitude to Professor Dr. Ahmed Al-Khatib for delivering an insightful session. Your expertise in wireless communication, channel modeling, and the role of machine learning in the massive MIMO system give us valuable knowledge and new perspectives. The clarity of your presentation of solving complex optimization problems have enriched our understanding and inspire us to explore further in this exciting domain. Sir has very well explained deep science, 6G, and digital twin technology. Thank you once again for your gracious presence and contribution to this FDP. Thank you very much, sir.
Thank you very much. Thanks, everyone. Okay.
Thank
And
you.
if you have any questions, anyone, please feel free to reach out. Thank you. Goodbye.
Now moving ahead with your faculty development program, we are honored to have with us Dr. Vimal Bhatia, sir, expert of our second session. He is a distinguished professor and researcher known for his significant contribution in the field of wireless communication, signal processing, and quantum computing. For formal inviting, I request Professor Prachi Jain, sir. I request Professor Prachi Jain, madam, to invite him.
Okay, sir. Thank. Sir, am I audible?
Yes, madam. You are.
Okay. Dr. Vimal Bhatia, sir, is currently working as a professor with the IIT Indore, India, and is an adjunct faculty at IIT Delhi and IIIT Delhi, India. He received PhD degree from Institute of Digital Communications with the University of Edinburgh in Edinburgh, UK in 2005. During PhD, he also received the IEEE Fellowship from Collaborative Research at the Department of Systems and Computer Engineering, Carleton University, Canada, and is Young Faculty Research Fellow from METI, Government of India. He is also a recipient of Professor S.N. Mitra Memorial Award in 2024, Professor S.V. Iyer Memorial Award in 2019, National Slovak Fellowship, and European Mobility Scheme for Senior Researcher at Czech Republic. He has worked with various IT companies for over 11 years, both in India and in UK. He is a PI, co-PI coordinator for external projects with funding of over 25 million US dollar from METI, DST, UKERI, and KPMG. He has more than 420 peer-reviewed publications and has filed 16 patents. He has supervised 27 awarded PhD theses and one PhD thesis submitted. His research interests are in the broader areas of communications, non-Gaussian, non-parametric signal processing, machine deep learning with applications to communications and photonics. He is a reviewer for IEEE, Elsewhere, Wiley, Springer, and IIT. He is currently senior member of IEEE, fellow IIT, and certified Scrum Master. He was also the Journal Co-Chair for IEEE ENDS 2018 and Journal Vice Chair for IEEE ENDS 2017. He has delivered many talks, tutorials, and conducted FDP for the World Bank NPIU TCube3 and invited talk at WWRF 46 Paris. He is currently Associate Editor for ITE Technical Review, Frontiers in Communications and Networks, Frontiers in Signal Processing, IEEE Transactions on Green Communications and Networking, and IEEE Wireless Communications Letter. He is currently member of Steering Committee for IEEE ENDS. He has been mentioned amongst the world's top 2% scientists by the Stanford University in 2021, 2022, and 2023. Now I request you, sir, kindly address the participants. Thank you.
Okay, thank you so much for the kind introduction and opportunity to be part of the FDP. Thanks to Professor Pant, Professor Jain, and the rest of your team. What I have done today, and all the participants as well, I guess there are a lot of participants online. So my talk today is split into I think there was some logistics issues, so I'm giving a talk today. So it's basically into three different slides. The first one will look at what we do in our research group. So some of you might be working in something similar, or you may be interested in some part of it. And you can feel free to drop a mail with a clear subject line on what you are intending to do, and we can take the things forward. So this could be extension of your research or our research, and then your student internships or some joint projects and all. So just feel free to get in touch. So the first set of slide deck is about our research group, what we work on, what is our area of interest. Then in this FTP, I have to give you an overview, I'll say, in the given time on 5G and 6G. So I've got slides which will initially go look into 5G, and then we will move on to 6G thereafter. Okay, so let's start. I'll share my first slide deck. Okay, let me make it full screen because it sometimes doesn't work properly. So I'll make it full screen and then attach. Okay, and then someone can just tell me if the slides are changing.
Yes, sir. Slides are visible, sir.
Visible? Okay,
Yeah.
so let me try and change it to the second one. Can you
Yes.
see? Okay, perfect. Okay, so thanks for the introduction, and that's I think largely already covered in the introduction part. For my research, I'd like to thank my DST and our other sponsors, Ministry of Education, AK Finland, TFK Finland, UK, IERI, Indo-US Science Technology Forum, EU, and others, for supporting our research for more than a decade at IIT Indore. Skip this slide that I usually use it when I'm giving a presentation abroad, but in India, I guess all of us know where Indore is. About myself, already covered too, so I'll skip this part. Except for that, yeah, I've worked in India and the UK in ICT industry before joining academia. So about 12 years in industry and almost the same 12 years in academia now. In a research group, we largely look into various aspects of communication and applications of signal processing, AI, ML, as well, not limited to communication itself, but other applications too. One of the larger, a part of our research is looking at performance analysis for beyond 5G and 6G. So we'll touch base on 5G and 6G and what to expect, what are the technologies that are, and what are the driving forces behind these two standards. Then we do work on adaptive signal processing. That was my thesis as well. My students are also working in adaptive signal processing or machine or deep learning. So some where we design or propose and analyze new algorithms for 6G and other applications. There's a small one slide on biological. I'll show what it is. I guess some of you may be interested, or you may do something, may already be doing something similar. Now, if you're from a communication background, you would have come across or worked on OFDM, I said MIMO, NOMA, cognitive radio, full duplexing, terahertz. So nowadays our focus is NOMA, terahertz, largely, and a bit of full duplex as well. Visible light communication is an alternative technology. If you're not worked, I have one slide to just give you an overview what it is, so you may be interested. It is a parallel standard, not a parallel standard. So it's a parallel technology. So similar to Wi-Fi when we say so. It has its own evolution of standardization, which is in parallel to 5G, 6G. So we'll see also, we will expect some standard to come, but it is a technology. The products are available in the market. Deployments in some commercial setting has already started. So it is no longer sci-fi. I think it is something which is happening at present. Then optical and quantum networks, will just touch base on this because this is something that will be working more for the next 5 years. A bit larger team now, focusing on various aspects of quantum networks, thanks to the initiative by the government of India on having a national quantum mission and a vision to connect the country north to south in a secure quantum secure optical network. We did one thesis on radar as well. I'll not go much in detail on it, and we do work with industry and defense over the years. Some of our sponsors and countries where we have been collaborating over the last decade plus, and currently we are executing projects with the UK, Taiwan, Sweden, and Finland. There's some of the outcomes from the research group, and some of our alumni from the research group, they are now faculty members at IITs, NITs, and triple ITs, or doing postdoc, or working for industry in UK and other countries. This is one application where we looked at advanced signal processing techniques and AI/ML techniques, interdisciplinary work, where we looked into viability of a seed, if a seed is viable or not. In particular, focus was soybean seed. So this was a work done with IIT based in Indore, and Soybean Research Center based in Indore. It's an ICR facility. We worked in this interdisciplinary area, and our focus came from AI/ML application for finding out if the seed is viable or not. This is the second part, which will not cover in detail today, but it is interesting, and should a telecom engineer must know that we divide our communication networks largely in two parts: a backbone network and the access network. Right, so access network we call it where the users are or devices are connected. For example, I'm connected to Wi-Fi modem, so this is the access part. If you're connected to a cellular station, base station, so you are that's the access part of the network. So ACCEESS. And then there's a backbone, a backhaul network, where which is largely an optical network. There has been on IAB and others, but largely still the this link is optical, because again optical fibers are more um, they can carry larger data with lower errors. So that's why it is preferred. And between cities, now with campuses, they're all connected to optical. Even at home, we get fiber at home, and then at home we use a Wi-Fi modem or something to make it wireless. But till our home, it is a fiber. So here our focus has been largely on resource allocation and routing, where we see, okay, if there's an earthquake or some other um, things like let's say a node failure happens, and how can we still give the user the service level agreements that has been agreed on. We still provide them the same, and so we worked on different resource allocation or algorithms and techniques and analysis for an optical network. Going forward, we are looking at securing this network. We already have supervised one thesis on it, and now more students are working, and the research staff is working on it. Is where we have this current optical networks, and we want to secure them. We can secure them using quantum key distribution, where essentially we have a traditional data channel, we have PICH, which is the public interaction channel, and then a new channel is introduced with the coming of quantum communication, so which is for quantum signaling channel. So here again, we are looking at various architectures, and there are different challenges that come with when the quantum key channel is allocated. So that's what our focus is, and will be for next few years. This is one work we did on mobile edge caching. Again, a collaborative work with India and UK. Here, if you look at from 5G onwards, we are looking at a heterogeneous network. So we have like a tower a mobile tower that you see, when in your city or when you go outside. So that we call it as macro base station, which has a larger coverage. But the data rates are smaller, and number of users it can handle is also smaller. Now, from 5G onwards, we're looking at this HetNet environment where we have a small base station. So we have 3 different bands in 5G, and there's a different slides, so we'll look into them in details. But basic idea here is, in this work, we looked at caching and algorithms, which are distributed machine learning based algorithms, where we predict and try to cache the content closer to the user. So some of the content is prefetched. Now there are certain challenges which are not there in the optical networks, but which are there in the communication in the communication network, because again this channel is changing very rapidly. So as compared to a fixed optical network or Ethernet based network that we have for computers. So, and then also again the compute and the memory is also lower. So hence there are different challenges. We looked at some of them and to solve them. Now this is a visible light communication system. So over the last decade or so, we have as a consumer, we have moved away from using incandescent or filament based lighting to the LED based lighting, right? So now we can use that LED for lighting and also for communication. That's the basic concept behind visible light communication, because we're using a visible light band for communication. It's again a license free, just like our Wi-Fi communication, but it uses the lighting infrastructure. So here, a very simple example would be we all use remote controls for our DTH boxes, or changing temperature or settings in our air conditioners and others. They also communicate using LEDs, but okay, they're not invisible band, but they are also using LEDs and very slow data rates. Now, if I can, expand this, or look at a glorified version, we can have all these LEDs, which can be looked into as different antennas. So so when you switch on and off LED very fast, to a human eye, it seems that the light is always on, but in practice it is no. It's a simplistic example I'm giving. So you can switch on and off very fast, but for human eye it seems like it is always on, but in practice it is not. It is transmitting zeros and ones when it is switching on and off, and each of these LEDs can be used as a separate antenna. So you get a MIMO setup from a very basic bulb that you get for 100 rupees or about a dollar or so, that you can get from the market. It also has 8 or more LEDs, and if I can control all of them independently, that's a MIMO setting. So it's a very easy setup, and low cost setup as well, compared to the RF based computer technologies. And it is green and secure by nature, but then there are different issues as well. So and this is something which started as a sci-fi, I can say, to many researchers as well. But now there are products, there are deployments that has happened in different in supermarkets. People have used their mobile phones as the receivers, so there's no extra hardware that is used. However, if let's say you want a higher data rates, then yes, you can use a dongle-based device, which we used to use some time ago when, or if you have to connect to your cellular network and use it as a hotspot, then we used to use a dongle type of device. Something similar is coming for VLC to connect with your compute. I will skip this part. Now, this is a technology which we thought would come into 5G. It is not made into the standard, but it's a very exciting technology running in parallel. So in 2013, there has been demonstrations on setup as well in our research lab. Also, we had a small NOMA setup, thanks to funding from MIT. So if you look at, but we are expecting maybe in the later version of 5G or 6G standard this comes in. If you look at the way the IoT space has expanded, and the number of devices that each of us are using has been exponential. So now I think now if 2025 we would be, I think, around 12 times more number of devices communicating than the human beings. Now, as faculty members in our coursework, we tell, yes, you can use a resource more efficiently by doing a multiple access. But when we say you do multiple access, we always say you go orthogonal. What it means, if I'm looking at time or domain, so I give one very small time slot to one user, second user gets another next time slot, and so on. I can have, let's say, 8 users having different time slots, but the full frequency band. Alternately, I can give them part of the frequency spectrum, but I can give it for the full time. Right, so that's the FDMA. The first one was TDMA, and there are other flavors as well. They're all code domain. Like in case of CDMA or spectrum, we use different orthogonal codes. So I have 8 users. Now, if I get the 9th or the 10th user, where do I fit them? Because I've finished all my orthogonal slots. So that's where NOMA comes in. We can squeeze in 1 to more number of users. Where, yes, once we break orthogonality, there is an interference that is added. But since it is in a controlled fashion, we can cancel it as well, because it's known. It's not unknown interference that has come in. It is known. It has been added purposefully, we can then, and there are certain rules how we do it, in what conditions we can do it. We don't do it in all the conditions. So once those conditions are fulfilled, we are able to cancel that interference and can support more number of users. And this is also more fair way. So for example, right now, when we mobile handset, um, we are all given the same resource. When you take a SIM from Airtel, and your friend also has a SIM from Airtel, maybe. Uh, but when both of you, let's say, are sitting next to each other, one of you is looking at a Netflix film, other one is the phone is idle, or maybe sending one or two messages on WhatsApp or SMS. So your requirement is very low, but your friend's requirement is very high. But both of you get the same resources when you take the SIM from Airtel. Resources, I mean, time and frequency slots. So it is not really fair for someone who wants more, but yeah, because it can't handle, but it still try to handle in the same resources, and the other person who doesn't need that much resource is still holding on to the time and frequency slots, but it's not using it fully. So it's not really a very fair um, or efficient allocation of the spectrum. That's where NOMA comes in. So we'll touch base on NOMA as a potential technology, because it has not made to the 5G standard. There has been studies, but let's see if it makes into the standard itself, or maybe it's a 6G standard. And then there are various forms which are helping us achieve the KPIs, or the key performance indicators for 5G and 6G. So one of the technologies is SWIPE, simultaneous wireless information power transfer. Basically, the technology um, tells you that yeah, you can uh, do communication as well as charging of the devices, or simultaneously, which is important for IoT and other applications where you need power. But how do you get the power if it's not possible to have a power cable run through the whole building, or bridges, or some places where it's not feasible to put them in. No, we looked at various architectures. I'm just going to skip this part quickly. And lastly, if you're interested, you can have a look at our book, which came out a couple of years ago, on 6G development, sustainable development, and for rural and remote community. That's available on Springer online as well. It was a joint initiative with Finland and India together, supported by Ministry of Education in India, and that's the outcome from that initiative. Now, this brings me to the end of my group overview slide. Now, any questions you can ask now while I'm changing my slide deck to the 5G slides.
Any question from the participants on the slides? Sir, you can proceed.
Okay, thanks. So yeah, we can then take it at the end as well. That's no problem. Okay, so I've made it full screen. I hope that is visible. Okay.
Yes, sir. Yes, sir, it's visible.
Okay, thank you. Thank you, Mr. Yeah. So I'll give you a small introduction to 5G, how we transition from 1G to 5G, what are the spectrum, what are the technologies that are there in 5G, and future of 5G, and then we look at whatever time we have left. We'll look into a sneak preview of also 6G, because again, the standard is not out yet. There's discussions going on. So, but what you can expect will come out. Now, 5G, unlike the previous version, it had a different vision. So 5G is seen as a platform for connecting virtually everyone and everything. Now, 5G is being designed with the flexibility and scalability in mind, because you see, flexibility, there are a lot of new applications that come up. So maybe when 5G standard came, there were a few applications. Future new applications will come. Similar thing with the scalability. As I told you about an IoT scenario, there's more, not more like it's a factor of 10 to 12 times more. So there is an expectation that even this will increase further, maybe 15 or 20 times um, before another 6G comes in. So we'll need to support that so many devices. Um, However, we have to classify our services provided by 5G in three different cases here. We do in 5G in three different use cases. The first one is for enhanced mobile broadband. So this is for a typical urban customer. And if you ask anyone, what do you need from a new standard, they will say, we need higher, data rates. Right. So typical urban customer uh, will be using this enhanced mobile broadband. Of course, rural as well, but largely the systems has or standards and things are designed for actually for the urban user. Then we have a mission critical control. So again, over the last few years, we have heard a lot about autonomous vehicle, autonomous drones, industry 5.0, so automation of industry. So that's where mission critical control comes in. So that's yeah, I should have I can get a pointer. Let me get the pointer so I can point it to where I'm. So yeah, mission critical control is a second pillar or vertical of 5G. Then it's a massive IoT. So here you're looking at smart cities, you're looking at wearables where it has sensors, homes, factories, and the cities outside, smartwatches. So there's a different type of requirements for this that we'll cover. But broadly, there are three different verticals that 6G that the 5G is designed to support. Unlike the previous version, so as I was telling you about Noma, so in till 4G, we had one band, so one radio head, and the same was expected to serve all the let's say, three different applications. But here, in case of 5G, we for three different verticals, we have different physical layer and other requirements that change. Some of the key deliverables for 5G is 10x speed throughput, bringing more and uniform multi-GPS speeds, 10 times more. So this is 10 times more is from the 4G standard. Right? So 10 times decrease in latency, so latency of 1 millisecond. So when we're looking at 6G, it's even 10 times more decrease. So that there we're looking at 0.1 millisecond or lower. Then 10 times more connection density, 3 times more spectrum efficiency, and traffic and network capabilities as well. This I can maybe skip this other slide which talks about the same thing. Yeah, this is the one. So here, if you look here in 5G and other, so 5G is the fifth generation of wireless, then NR is new radio. That's a terminology used. Now here, if you look at, there are three different applications: massive IoT, mission critical control, enhanced mobile broadband. So enhanced mobile broadband, typical urban user, it needs extreme capacity, so 10 Tbps per kilometer square, so extreme data rates, 100 megs plus, speeds, deep awareness, so discovery services where the sensors and things are. Then we have a mission critical control. So this is for the industrial applications or secure application, like strong security is needed for if it's a government, health, or financial services. Ultra high reliability, so 1 out of 100 million. So if you're working on autonomous vehicles, then you would not like to have any system failures, right? Or any packet being lost. So here the requirement is 100 million. So 1 million will be 10 lakh if you look at the way we do it in India. So about 1 million is 10 lakh. So this is a crore and this is 10 crores. So in 10 crores packets that are sent, so only one is lost. Ultra low latency. So here also this one point which is not mentioned is uh, we have multiple of these radio heads, multiple connections also possible in 5G. So if let's say one connection goes bad, we still have another one. So we have a highly available system, and that's what you need. If you are going to control a drone or autonomous vehicle, if the primary communication link fails, what do you do? So that's where ultra high reliability comes in. The ultra low latency, because you have to respond very fast. So like in industrial setting, if something goes wrong, then corrective action has to be taken very quickly, or all the other machines has to be switched off or paused. Same thing for autonomous vehicle. If there is a brake has to be applied, so the command has to go there in a 1 millisecond duration only. Now there are two extremes here, but I gave you two examples as well. So extreme user mobility. So for example, you have drone or even a very high speed train being controlled, so or communicating. So there's extreme user mobility. On the other hand, there could be like an industrial setting where the machines are not physically moving much. So once you put a machine, you put the sensors, you get the communication network ready. It is not going to move. Yeah, machine inside there might be some process that may go on. So it has to support both extreme user mobility or no mobility at all. Now the third important pillar or vertical is massive IoT. So there's a deep coverage, so it has to get to the different locations which are difficult to get otherwise. Ultra low energy. So from 5G onwards, we started to see this energy being mentioned as well in the standard. So 10 years of battery life. Now, as a mobile user, uh, we charge our phones at least once in a day, right? So this KPI is not for like an enhanced mobile broadband type of application, right? So here we're looking at 10 years of battery life. Now again, battery technology may not support this 10-year of battery life. So how do we fulfill this KPI? So the alternative would be using swiped or some energy harvesting type of techniques where you can have a sensor which is, let's say, sleeping. So you put into sleep mode. When you need the information, it gets activated and sends the information, and then again goes back to sleep. Right, so that's how you can save a lot of battery, because the RF components, so that take a lot of battery power. Synchronization takes a lot of battery power than the typical signal processing chain. Then we have ultra low complexity. There's a 10 bits of per second. So here, if you look at IoT type of application, what we're saying, we have a sensor. The sensor is a temperature sensor. So it is only sending a few tens of bits. So it's unlike the extreme, data rates like enhanced mobile broadband of 100 plus megs. It is only tens of bits per second. So if you have to send, so for example, use your this SMS message. If you send, it's only a few kbs of information that needs to be kbs of information needs to be sent. When you use a remote control, you're sending very small bits of information. So here in IoT also you have a sensor which is sending temperature, humidity, or other physical measures. So it doesn't need so much bandwidth. Then there is ultra high density. So we may have lots of these sensors. So for example, let's say you have a campus where you want to know what is you have this automation system. You have different sensors sensing, let's say, temperature, lighting, lumen levels. It is also checking the humidity level. So then it can adjust your air conditioning or lighting in the buildings. So those are very small sensors which are giving very small battery, but there might be many of those sensors per kilometer square. So for example, smart cities and other applications, we might have lots of these sensors. The figure here on the left hand side also shows similar thing, but in a different form. So here we have ultra reliable low latency communication, um, massive machine type communication, enhanced mobile broadband. So here we started, with voice is somewhere in the middle here. And as mobile broadband, we need GBPS information. Smart or e-buildings, we need IoT type of applications. Smart cities, we need more sensors are there, or machines are talking to each other. Then ultra reliability will be industry automation, mission critical applications where you need an alternative. If one thing fails, you need an alternative. So that's why it's called as URLLC. You might have heard about this word, or you will hear this word when you talk in the 5G lingo. So that's ultra reliable, low latency. So the latency is small, but reliability is very high. So for example, you're building a controlled or as a communication system for a drone or a autonomous vehicle. You will have a highly available system. So you'll have not only one link but another, because if one link fails, then you have a problem. So that's why it comes under the same category: ultra reliable and low latency communication. Now, what are the technologies that are driving 5G NR? So for mission critical control, we use a low latency with bounded delay, because here, we can't really afford to wait. So for example, if you have to control an autonomous vehicle, you have to brake. So it has to be in the bounded time. Right? If it says within 1 millisecond, it has to within 1 millisecond. However, let's say you're watching a film or a cricket match or something, then even if the packet is delayed by more than 1 millisecond, it doesn't harm, because as human beings will not be able to perceive. If let's say there's a big attachment to your email, then even if it takes a few milliseconds extra, it's okay. But applications where there's industry involved, there is a need for immediate action, then mission critical control type of applications would be there. So we use low latency with bounded delay, we use efficient multiplexing, nominal traffic, grant free uplink. So try to remove a lot of um, a lot of overheads when we're doing uplink transmission. Yeah, because it's ground free, so there might be collisions may happen, but then again randomly we can again send the information back to the uplink. So also because again we will reduce a lot of this overhead, so it is faster, right? Simultaneous redundant link. So this is something I mentioned. So in 4G we didn't talk about this. So here in 5G it's simultaneous redundant links. So if one link fails, another link takes over. Then reliable device-to-device links optimized and pilot for this application. In case of enhanced mobile broadband, so there was a previous talk on MIMO channels in MIMO as well. So that's where it's a typical urban user, we can say, looking wider bandwidth, mobilizing millimeter wave, because millimeter wave gets you to a smaller distance. With mobility, there are challenges. So that's why I said we're trying to mobilize the millimeter wave for the enhanced mobile broadband applications. Shared spectrum, then dynamic, let's say massive MIMO. So the previous talk was on MIMO and channel modeling, and also you can, so massive MIMO is which here now in 6G we talk about ultra massive MIMO. So that's another scale of things. Again, advanced channel coding schemes that are very important for error correction and communication. Massive IoT. So here it's low complexity narrowband, because it does not require a larger bandwidth. It needs very small bandwidth, but it has to be a low complexity. Low power modes for deep sleep. As I mentioned that yes, you can have a sensor that goes into deep sleep, and you wake up the sensor, oh, now it is time for you to send the information, it can start to send the information back. So basically, when you do it, you are reducing the interference and also largely reducing your battery usage. So for example, a sensor has to send, outside ambient temperature, which does not change very fast, so it can send in 1 hour, 2 hour. So it doesn't need to be on always, right? It can get the information and then temperature sensed and then send it back. Efficient signaling, because again, there's a lot of overhead, grant free, optimize link budget, and manage multi-hop. Okay, so how we got there to 5G? What we see that every 10 years, approximately every 10 years, we have a new generation of wireless communication, or mobile communication. We started with mobile voice in 1G. Then we moved to efficient voice to reach billions in 2G. 2G still is very popular. One of the standards which is large, which covers a very large land across the world. So that's what we've seen in India as well, right? Now we get 4G, 5G, and 2G. So 3G is largely not there, but 2G still have survived. Then 3G is was about wireless internet, shifting towards mobile data. 4G was mobile broadband, emerging expansion. We can do, these courses online because again, 4G bandwidths are good enough. But it wasn't started in around 2010. So LTE, LTE advanced, the standard comes from the 4G. Then 5G is seen as a unified future-proof platform. So here the industries will connect virtual reality application, mobile phones, vehicle to vehicle, vehicles will connect, industry automation. So there's many applications that connect to the 5G. So it is seen as a unified platform and a future-proof platform. So this is was in 2020. Say 5G new radio. Now the foundational technology is not that when, let's say, 5G comes in, or let's say tomorrow 6G comes in, it will change everything in it. No, we have trusted, stabilized technologies that we like to use. So one of the survivors, I'll say, is OFDM. It was very popular in Wi-Fi, made into 4G, made into 5G, and maybe will make it into 6G as well. So OFDM, flexible framework design, mobilizing millimeter wave. But this has come with the technology which has been given before. So now, if you look at the data rates that are expected, so for example, in the 1990s, we were happy with the voice itself. Megs was a luxury. Then in 2004, 2005, Megs was still a luxury, I'll say, getting about kbps. Then we had foundational work for LTE, OFDM, more antennas came in support. So we still had, let's say, a MISO kind of system where we have multiple input antennas and single output antennas. So your single output here I'm looking at is your handset, your mobile phone, which has only one antenna, but there are multiple antennas at the transmitter. Going forward is GPS and multi-GPS. So we 2018, 2019, and 2022 and beyond. Various technologies like multi-edge, LDPC, reciprocity-based massive MIMO, scalable OFDM, and others, and mobile millimeter wave. This is how the standardization took place. So 3GPP, it's a body which is carrying the same name. It is a standardization body. So you can think of it as, let's say, a United Nations of telecom people. So it makes different standards for communication. So around 2015, the branch off happened for 5G. So 4G to 4.5G are seen as evolution, but 5G is seen as a revolution. And fast forward now to where we are today, 2025. So now we are expecting the 6G branch off will happen. Yeah, this year, hopefully. Yeah. Now, yeah, okay, there it's a marketing thing, but basically, if you look at different bands, as I told you, for um, till 4G, it was the same cellular bands that we have been using before. Okay, there has been some version of LTE that works on ISM, but still largely it is the same bands as before. However, from 5G onwards, we started to look at in gigahertz bands as well. So that's where the millimeter wave thing comes in. So the roadmap was for different bands. So 28 gigahertz is a very popular band. Some places like Japan and Korea also looked at 4.5 and 3.5 gigahertz. EU and China on 3.5 gigahertz. Um, Standards then rolled out around 2020. We had the first. So the first initially it is using the same bands like 7 to 800, 900 bands for VHF UHF communication. So same thing is here as well. Um, However, in US, okay, they said you can use 2.5 gigahertz to I can possibly skip this. Yeah. So if I see how we got there, so transition from 1G to 4G. So 1G we had bulky handsets, they're expensive, spotty coverage, and inefficient use of spectrum. 2G, we had lower data rates, high delay, low coverage area, inefficient spectral use and power consumption. 3G was spread time for spread spectrum, so everybody got the same spectrum, but then there were different codes, so they could communicate orthogonally. So again, this was used to get up to 5 to 21 megabits per second, and operational frequency was on 1.8 to 2.5 gigahertz. So close to our ISM band. Then 4G came with better mobile broadband. So FDM, MIMO, carrier aggregation, Harada modulation. So there's a lot of these new things came in. And uplink and downlink speed of 500 to 1,000 Mbps. Depends if uplink or downlink. Then packet or message switching, operating frequency around 2 to 8 gigahertz. Now, this another thing which is largely overlooked is in 5G. So in 4G, we had one radio connection at a time. In 5G, we have multiple radio. We can have multiple radio connections at a time. So that helps in the URLC type of applications. This may not be required for IoT application, but that's okay. But they all come under 5G. Now, in 4G, there's a single network for broadband video and machine type communication. Now, in case of 5G, we have individual slices for different needs. Then, in case of 4G, there were first steps into cloud, so CRAN and all we were hearing. In 5G, it is going to be even more move towards cloud. Now, this slide basically tells you the impact of different frequency bands. We can skip this as well. That's okay. Yeah, this is also okay. This was from content, so this came out. So we have new architecture, distribution processing, AI content. So the search goes on. Right. So we had these three things. So millimeter wave, centimeter wave, and wide area for LTE M. Massive MIMO, beamforming. That's one technology that is important for 5G and also for 6G. Skip this part. And this is how the global rollout happened. And interestingly, so till 4G, you can say that largely the the Asian or developed countries were taking the lead. So we had like Korea, Japan's like they're taking the lead in on the western side, and then US as well. Whereas for 5G, it was the picture changed a bit. So there's like, say more prosperity in different parts of the world. So Middle East came out to be one of the newer regions, which took up 5G quite early. Of course, South Korea, China, Japan, they are already ahead in these deployments. And initially, it takes a lot of time to uh, get the systems fine-tuned. So you may have, let's say, initially a 5G a network, and you're, let's say, connected to a 5G network, but at that time, the system may not be stable. So you may have call drop, you may have other issues that come up, but over the period, the system gets stabilized and the parameters get fine-tuned. Europe, as such, yeah, we expected, and yeah, it is one of the first movers. So Italy being one of the first movers, and Finland and others being the first users. An interesting aspect was the Middle Eastern influence. I think in India also it was not very far, and that's what is happening. When the 2G, 3G technologies and 4G were introduced, we got them pretty late as compared to when they were launched. But in 5G, that duration came down. So from 10 years, we can now roughly, I think, around 3 years, and 6G, we may be doing it at the same time as the rest of the world. No, okay, there should be, yeah. So spectrum, three different spectrum. We can maybe skip this one. So here, we can work on licensed or unlicensed as well, so it can help both. No, this is slide I wanted to touch. So we have, it has a deep, a rule of thumb, and then there's a formulation as well. But basically, the lower the frequency, it can penetrate through the walls. It can travel a larger distance for the same power. And for the same power, if you move to, let's say, millimeter wave, so you move to mid-band, or let's say millimeter wave bands 26, 28 gigahertz, as compared to, let's say, 900 megahertz. The 900 megahertz for the same power will give you higher coverage. However, the data rates are smaller, right? So we see here it's about 100. In case of millimeter wave full, it is 10 GPS. So there is a difference in the peak data rates, and the use cases are mentioned here as well. So we have deep intro coverage, supplementary uplink coverage layer in mid-band. We get coverage to LTE, major commercial bands, and then Japan, China, Korea. They're all taking leads there in different countries as well. Because you can be, let's say, a South Korean, a mobile operator, you want to do it in India, so yeah, you can always go ahead and purchase that license. So if I come down to millimeter wave, we are looking at 26, 28, 29 gigahertz. Hotspot has a range of 400 meter square. Peak data rates of or 10 Gbps. Now that's not expected from the lower band, right? So bandwidth is also quite high for the millimeter wave. So we going to look into that context. Now this figure, yeah, there's another one which is better. Yeah, this later. Okay, yeah, this is the one. So here, so this figure shows that you have a small cell, which is a small base station. This base station might be working in the gigahertz band. So that's what, and we're looking at a multi-mode device. So we're looking at 5G, 4G, 3G Wi-Fi. So in India, what we generally nowadays don't get a 3G support, but we get 5G, 4G, and Wi-Fi. So one handset will be able to cover a different distance and different standards. Now, if you look at a macro base station, so this shows it's a 4G LTE or 5G below 6 gigahertz, so that it cannot travel for larger distances. So a 4G macro station, then we have um, on the small. So if you look at the small cell, so this is like a small base station. So it has a larger bandwidth, but has a higher carrier frequency as well. So it can cover a smaller distance, but with provide a very high bandwidth. Right. So this figure shows that we may have a handset. We already have handsets which are supporting multiple standards, and this was all the vision about. Okay. What are the technologies? Will not be able to go in detail, but maybe in the other sessions you would. So massive MIMO, low latency, enhanced broadcast, NB-IoT, so narrowband IoT, device-to-device communication, a very high modulation, orders, advanced MIMO. So there are many different techniques that can be used by the future standards 5G and also going forward for 6G. So for example, yeah, there are different considerations. So antenna is, let's say, MIMO or 3D MIMO of antenna. Uh, Waveform multi-carrier OFDM, windowing multi-carrier single carrier waveform as well. Reliability, signal punch ring and reliable links. FEC, again, the typical ones, you get LDPC, polar, turbo, ports, and others. Slicing is another thing we missed. This is slicing, which is important. We do slicing in the layers for optical network already, and this concept is into the access part and also the backbone part. Now, 5G adapts different spectrum, so low band is below 1 gigahertz, longer range, massive IoT type of applications. Mid band is a wider bandwidth for um, MBB or mission critical control. Then we have higher bandwidth around 24 gigahertz for extreme bandwidths, extreme data rates. Now this talks about different type of technology. So OFDM-A is the one that is still there. That's what you have a 5G handset. You will be using OFDM right now. But then there are different other discussion of flexible frameworks, looking at NOMA and NOMA flavors, SCMA, RSMA, and others. Then we have yeah, different file. Maybe let me come to this one. Yeah, this one is better. So it tells you about the key requirements for the EMB uplink and downlink. Key requirements for wide area IoT. So for example, if you look at wide area IoT, we have a different requirement for uplink and downlink. Okay, or we can have it common. So for example, key requirements are it should support short data burst, because if you have a sensor which is sensing some information, it is collecting it and then sending it. So it is coming in burst, very small burst, small data rates, but it needs a longer battery life and deep coverage. Whereas on the other hand, we have so single carrier FDE, RSMA can be used, or no more other forms. But again, as I said, no, they didn't make it to the standard, so we'll have to use what is available in the standard. FPMC is another technique that has been discussed. It's a good research topic as well, but somehow it hasn't made into the standard yet. It is more efficient than OFDM. OFDM, you waste about 70% of the energy, but here you can save it. But then the implementation is complex and it has not made it to the standard, so it's not available in the different products and so maybe in 6G, I don't know, maybe one of the new modulation schemes could be that, but I really doubt that it will replace OFDM. So OFDM, I think, is there to stay even in 6G. Now this is about NOMA. So you can see FDMA. So the full frequency band is allocated. X is time. So for the full time, the slicing of frequency has happened. If we look at TDMA, so we give a complete time. We have a time slot, but we give the full frequency is given. Typically, what happens in practice is this: we do frequency hopping. So we give you a time and a frequency slot, which again keeps on changing. And as a user, I don't know that it is changing, but in the background it is changing. Then we have RSMA. type of RSMA or NOMA. So RSMA is one part, SCMA, Musa, those different names, but ultimately is NOMA. So you are giving, so these different colors, they show different users. So you can have multiple of these users given the full time and full frequency, and some clever techniques to cancel this interference from the new user that comes in. So yeah, that's again pretty much it, I think, for the 5G part. Yeah, massive memory already had some, thing. But then again, there are various challenges. Again, this shows no beamforming, and also there are various challenges, including beamforming and others. So massive MIMO. These are some technologies like beamforming. We need to do millimeter wave dense cells, so it will support M2M. M2M is machine to machine, device to device, D2D, IoT, connected vehicles. So those all services are enabled through 5G. Same thing for IoT we discussed. So yeah, this is largely, I think, I can cover in 5G. Again, if there's any question while I'm changing my slide, then please ask. I'll move to the last slide deck. So these are these slide. Oh, sorry. Yeah, sorry. So now this is adaptation of slides with our 6G research partner, the 6G flagship program based at Oulu University in Finland, the birthplace of Nokia, you can say. So I'm going to attach that slide deck. So we have been researching. Okay, stop presenting. Yeah. So we have been researching things since 2018 closely with the group and different researchers. So yeah, there you go. Okay, so this will give you a overview, say, of what to expect in 6G. So these are slides adapted from the 6G flagship program. So now it's a curtain raiser. So we look at the vision, introduction, pioneering research. We look at connected technologies for 6G, visualization of 6G, what to expect. Now 6G is a vision for 2030. As we saw in the previous slides. So every 10 years we expect a new standard to come in. So this decade you can say is for 5G. We already have 5G base stations installed. We are using 5G in India in most in many places. But then as researchers and engineers, we are gearing up for the 6G era in 2030. So where our society is, we're already saying it's largely data driven. Now the focus for 6G is to bring things. Okay, there's a global, but then there is a local and hyper local type of vision as well. So enable near instance kind of unlimited wireless connectivity. So some of the expectations which were from 5G could not be fulfilled. They came into 6G and fused with the AI inspired application for the society. So here in case of 6G, so we have, as I said, the vision is global. Then we have regional, wide, hyper local, and hyper local. So this is now in 5G, etc. We had this fundamental shift of looking at different frequency bands, supporting multiple radio heads for different applications. Right? So your handset may not be designed for what it may still say 5G, but it may not be able to support all the three technology verticals. It may be okay for enhanced mobile broadband. That's okay. It still is 5G, but that was not an option like for the 4G case. 6G is going to build on the top of it. So we have a local specialization and then hyper-local specialization. But here in 6G, we are seeing the requirements are driven by the United Nations Sustainable Development Goals. How do they come together? Let's look at the next slides. So here we say the key drivers for 6G are, we have this soft and the hard values meet. We call them hard is the technology or enablers, like the engineering requirements. And when they meet the software requirements, when we say soft, it is the societal challenges, like no poverty, hunger, education, no hunger, education, life uh, inside the the ocean, so below the water as well. We need to look for sustainable development. So United Nations comes up with these sustainable development goals, and in 6G the vision is to meet those goals through technology enablers. When we again repeat, so soft would be the societal requirements, and then hard will be the engineering requirement. That's what we as researchers come up with, and we measure any device or thing that comes out. Now, societal challenges are many, like 17 here are one. So no poverty, zero hunger, good health. So how can technology enable these requirements? So life below water, life on land. So now these can be through energy decarbonization, global environmental things, food security, food systems, sustainable and just economies, human life well-being. So how can this be done? So in 6G, we look at these different dimensions of data, compute, and energy. So till in 5G we started to talk about energy, but before that, this was not a major KPI that needs to be met. So now we have energy as a key point as well. So we may have a lot of data, we may have a lot of compute, but we need to do it efficiently. So we need devices which are taking less energy. How the evolution? So we looked we looked at the 5G slide. So we got up to here 5G and 6G. It is expected to be even higher data rates. So we're exploring new spectrum. So here on the research side, looking at even terahertz bands. There'll be some disruptive technologies. I think IRIS, ISAC, and all they are now can be classified as disruptive technologies, which were not there before. Even in 5G, it was not thought about. Cell-less network, disaggregation and virtualization, energy efficiency, and AI. AI is an important part of 6G. Okay, we can skip this. Yeah. So, is it naive to say, from that 5G is engineering to 6G for humanity? So, for example, if you look at this, okay, so I think I lost my pointer. Yeah. So here, if you look at sustainability goals, we have societal challenges like education, innovation, societal services, health and well-being. Societal goals will be like there'll be no poverty, good health and well-being, climate action, zero hunger, decent workspace, and economic growth. When you look at productivity in vertical industries, we look at health, manufacturing, financial technologies, education, and all. What now, as engineers, as scientists, we can see, okay, these are the requirements. How do I fulfill those requirements? No, these are the technology enablers. For example, you have RAN agnostic, automatic orchestration, non-device centric communication, extreme URLLC. URLC was for ultra reliable, low latency communications. Right? We look at newer bands like terahertz band. we look at security for cyber physical systems. You look at zero energy communication, so very low energy being taken, advanced signal processing or photonic based signal processing techniques. So these are all or in our hand, or in something as engineers and scientists we work on these problems, and in as a outcome we are solving some of these societal challenges. But here in 6G, the idea was, yeah, from the very beginning we look at those and societal challenges and then bring them to the engineering requirements. So the KPIs, so in 5G, in many of the KPIs of 5G are still valid for 6G. However, KPIs, so key performance indicators, must be critically reviewed and new KPIs be seriously considered. For example, if you look here, your latency, jitter, so they were there before, um, but they need to be, so for the cost KPI, energy KPI, so they need to be looked into as well. And these are the technology or the engineering, KPIs. Then we have the societal KPIs, like transparency, very important for AI. Ethical issues, that's very important. Privacy, trust KPIs, very important for AI-driven society. Now, these are some of the engineering KPIs. So, or wish list. So we have like a peak data rates of 100 gigs to 1 Tbps. Then we have radio latency of zero point 0.1 milliseconds. So when we were looking at 5G, it was 1 millisecond. So it was mentioned is a tenth of the 4G. So here also it is a tenth of the 5G. So we're looking at 0.1 millisecond. Very small. A battery life of 20 years. So in 5G, we're looking at battery life of 10 years. So here it is looking at battery life of 6 years, 20 years. So that is something, again, as a common customer, we will be charging our phone every day. So it is again going to be for very specific applications. Okay, not all the applications. Then positioning, 10 centimeter to 1 meter, so indoor and outdoor. So this is again very important requirement that has come up. Uh, you know, Again with autonomous vehicle, robots, and all. There's a lot of uptake on warehousing, and also that's where the localization is becomes very important aspect. So, for example, you have Amazon and Flipkart have very large stores. So they want to find out, okay, the product is somewhere here with the accuracy of say 10 centimeters. So should be able to do guide a robot or something there. So positioning is very important, and that too, if we look at the 3D position, 2D positioning, so we have GPS and all. Okay, not that accurate as compared to the cellular network. But then there is another challenge of azimuth. So the height is also or altitude. So that's also an important factor. Is that again a very advanced research problem. Again, 10 times more energy efficient. So, and some of these contradict as well requirements, right? So we've seen in 5G as well, we have 3 different verticals. So for example, if you need a very high data rates, and then we say, oh, we need ultra high reliability, we need maximum 1 out of a million outages. So now this will require higher energy. So it cannot be very energy efficient. This is only for specific applications. Some of these will be picked up. Right. So for example, IoT, I don't need 100 gigs. I don't need even 1 meg as well. It's only a few kbps or a few bits of information. Different stakeholders are there. Probably skip this part. I think we can skip this as well. So this is something I wanted to cover before we stop. So this is important. So this is a roadmap to edge intelligence. I talked a little bit about our research on edge intelligence using MAC for mobile edge caching. Um, MAC is largely used for mobile edge computing as well. So caching, okay, is part of it, and then other things as well. So we are moving this AI to the edge, to the user. Now, this is what we are expecting from 5G to the 6G, which will happen from the AI perspective. So initially, let's say here it was 2020. This is the path that we have to take. So there's some pre-trained engine. We do transfer learning and do some. We can do some edge AI work. They're not looking at dedicated hardware, so we're looking at GPUs and all. Then distributed AI. So, for example, federated learning in order to reduce latency and all. Then we are using learning driven communication. So that keeps also reinforcement learning and other things where it is going to learn from experience and then improve. Security and privacy. This is a important KPI which was not considered in 5G, but this is important. Not secure and private privacy is an important consideration, especially when we are looking from the AI point of view. So, there are various challenges that have come up. Societal challenges. Okay, one is technological challenges that as engineers we try to solve, but societal challenges and change to the way we live and our laws and things are driven. So, for example, there are societal questions that are being asked. Is let's say we had that medical record or credit card details and all. They're very confidential and sensitive. Now you have AI running on the network, and AI somehow leaks this information. So there's no human being involved. So in that case, you see who is responsible, and how first of all how can we prevent it, and then who is then responsible for this? Is it the programmer, the researcher who wrote or devised this AI? Is it the company which is handling the data? It is the IT system company, or who is responsible here, and who's going to fix this problem? Then similar thing, questions are asked about to see if there is autonomous vehicle and that has an accident with another autonomous or human driven vehicle, then again then who is then responsible? Is it the owner of the vehicle, or the someone who wrote the software, who did the testing, which company provided the AI chip, or company that provided AI software, or the automobile manufacturer? So who will ultimately be responsible for anything that happens? So currently you see we have a driver in the vehicle, so we can always trace back and can put the responsibility on it. But now what happens when it is autonomous? There's no human being, right? So there's these societal socio-legal issues that are important to be looked into as well when we talk about 6G and AI. Okay, real-time training is another important. Then nanophotonics. Now this is a important area that we ourselves don't work, or no friends in researching in silicon, and will SI they are more up for it. Now this largely means is you see, if you look at the current systems, we even if you have a cyber physical system, or even let's say optical networks, we get the information in optics or optical domain. We convert to electrical domain using some form of transducer. We do some processing in CPU or GPU, some signal processing and things we do, filtering, demodulation, and others we do, error correction. We do all of these in electronics and in our GPUs or CPUs or FPGAs. It's in electrical domain. And then we again go back to the photonic domain if I have to transmit that information. Now, we can possibly do all this in optics directly. There's a separate branch, and there are a lot of researchers working on it. So if I receive some information from optical fiber, I have to do filtering, demodulation. I do everything in the optics itself. rather than converting to electrical and then doing all the processing and then converting it back. It will be faster. So nanophotonics is an important area, and this should lead to a 60 edge by 2030. So we're looking at AI is a very important part of 60 and beyond. I will not stop here. So we will be using AI in it. So this is the more important slide. So rest are okay. We can maybe even open for questions also. So basically, this is showing the development of the standards and how long it took from tech specification vision to deployments. So each standard, this life cycle is getting shorter. 6G is also, so we had this COVID era, so we lost a couple of years in there, but still for 6G, it is seen it is going to be 8 years or shorter from vision and technical standards to the deployment. Because it's a full life cycle, it takes a lot of time to do the development and then the deployment. So the development really happens when the discussions on standards are going on, but then deployment takes its own time. So around 2028, we are expecting maybe some pilots will start to come in. By 2030, we should start to get some deployments that will start for 60. Yeah, and then various verticals, industry verticals. For example, in 1G, 2G, it was largely the voice. 3G, 4G was connecting billions of mobile users. Then 5G and beyond was like trillions of connected objects. Now we're looking at applications like logistics, retail, agriculture, Industry 4.0, healthcare, sustainable development, automotive, and transportation. Um, and yeah, so then these are like URLC, and also these requirements will be different. But so URLC for um, a drone or autonomous vehicle is different than for an IoT type of device. So actually, we don't need URLC there because largely it is very small information that can be resent. It doesn't matter if it get lost; it can be sent again. So there are these customization that will happen for different applications. Right. So now, yeah, if there's any questions, maybe we can open. Is it okay?
Any queries from the participants?
So this is a comparison of what we have in 5G and what we expect in 6G. These are the engineering requirements. So, it's engineering requirements. So, for example, peak data at 20 GPS, and we're looking at 1 TBS. So it and the connection density of 24/6, 24/7, so a factor of 10. It's huge. Okay, so we looked at in till 4G said IoT, then 5G say Internet of Intelligent Things. In case of 6G, we say intelligent Internet of Intelligent Things because it is enabled by the edge AI. So terahertz, ANAT. So there are various techniques and technologies that are going to be driving this. So, and yeah, so we can maybe open any questions we can take now.
Any queries from the participants?
Hello, am I audible?
Yes, sir.
Yeah, good evening, sir.
Yes, sir. Please ask the query,
Um,
sir.
yeah,
Sir.
Vimal sir, I'm having a question actually. Sir, can we expect some more advanced modulation schemes for this sixth generation communication?
Yeah, hello. Yeah, can you hear me?
Yeah, yes, sir.
Yes, sir. You are audible, sir.
Hello, Prashant, you are unmuted, but the voice is not clear. Voice not coming. Or participants, if there's any questions you wanted to ask about
Bhavesh sir, you can ask the question
5G,
now.
6G in general,
Yeah, sure,
so
sir.
you can feel
Sir,
free to
can we expect
ask me,
more
type in
advanced
the
modulation schemes in sixth generation communications?
chat box, or you can unmute and ask.
Bhavesh sir.
Yes, sir. I'm putting the question in the chat box.
Sir, he want to know that the 6G modulation techniques.
Yes, exactly, sir.
Vimal sir, can you hear me, sir?
So this is some of the radio challenges.
Am I audible, sir?
Hello, participants. Yeah, okay, I'm getting some. Okay, there's some queries. So can we expect some more advanced? Yes, you can. In fact, we have been researching on these as well for about a decade now. Um, um, they may not come into the, you see, they may not come into the standard as yet, but there are many, newer modulation schemes. So, for example, we have been working on hexagonal comb. We're looking at higher order of hexagonal comb. These are 3D type of constellations that we can explore. So it's like a honeycomb type of structure. There is a research paper, well, less one research paper, but in fact, our research group has done a lot of research on this, on hexagonal comb, than I guess anyone else in the world. Um there is a very simplistic, and I think it's an open access journal which tells you what is hexagonal comb, how it is, and what advantages we get from it. It's very energy efficient also, so you can have a look into. You can go to my Google Scholar, just do a search on hexagonal comb, and there are other competing alternative modulation schemes also coming up, but this is something that we have worked on, so I can tell you about it as only. Yeah, so email ID, yeah, I can type it here, but you can also get it from just doing a simple Google search. I've just typed my email ID. So whenever you are sending, or student is sending email, I request please put a proper subject, because sometimes they end up in the spam folder. So yeah, it's better if you just put it clearly in subject line and inside text as well.
Any other query from the
Okay,
participants?
okay, thank you so much. Maybe I'll switch off the slides, stop sharing.
Any queries from the participant side?
Yes, sir. Sir, one more question is there.
Okay, so I think Mohit sir has put a form for the participants. This
Hello, sir.
form, so
Yeah,
we
Bhavesh
have
sir.
got lost.
Hello. Sir, I'm having a question. As you have already told
Okay.
that the
So
sixth
if there's
generation
no,
communication.
so I think Mohit said, I think you're unmuted, but somehow we can't hear you. So if
Okay,
it's okay, then yeah,
I'm
you
putting my
can
question
maybe
into the
sign
chat
off
box,
and
sir.
the participants
Yeah,
can
okay.
uh, take a break as well. So let's thank you for giving this opportunity, and we will be in touch somehow. Again, sir, yeah, you're unmuted, but again, your voice is not coming. But that's
Thank you,
okay.
sir. On the
Uh,
behalf of
we
the
can be in
participants and
touch
from
through other means. And so, thank you all the participants for patiently listening and for your queries. I have posted my email ID as well. So if there's any queries, you may get in touch. Or you can look, visit the Google Scholar and see, what we are doing in the recent years. And if something is of interest, you can always contact us. We still have the positions. We have positions advertised for in JRF and PhD in our research group, be it full time or part time. Um, in largely in wireless and the quantum era. No, no, Moichi, audible.
am I audible to you, sir?
No, no, Moichi, you're not audible. We can see you, but yeah, you're not audible.
On the behalf of participants and from MIT Group Institute, I extend my heartfelt gratitude to Professor Dr. Bimal
Some
Bhatia,
issue.
sir.
I think other participants are also not audible.
You
Well,
have
both are audible, it says. Oh, so is it
okay.
some
Thank
problem with
you,
my
sir,
system
for
or
your
what?
valuable time, sir.
I don't know. Okay, maybe
Okay, thank you, sir.
increase the volume. No, I increase the volume. Somehow I'm not. Yeah, yeah. So, Mohit, do you? And someone mentioned both are audible, but for some reason, yeah, I can't hear you. Okay, thank you,
Thank you,
Moichi.
sir.
Thank you so much. So have a good evening, and thank you for having me over, and all the best for the upcoming. Okay, okay. Take care. Yeah, bye bye.
Thank you, sir.
Bye. Namaskar. Yeah,
Good
good
night, sir.
night.
Namaskar.
Thank you.
All the participants, you can fill the feedback form. I have already shared in the chat box.